Hello there and welcome to Life Beyond Seen, where curiosity slows its pace, complicated ideas are given room to breathe, and science is explored in a way that lets the mind unwind instead of race. Tonight, we're turning our attention to a body of water that, at first glance, seems ordinary, wide, blue, familiar. A place for summer holidays, fishing trips, family photos and quiet horizons. But beneath that calm surface lies a record that has earned it a reputation few inland waters would want to claim. We're talking about Lake Erie, often described as the most dangerous of the Great Lakes. It does not look especially threatening. There are no towering cliffs surrounding it, no obvious whirlpools spiralling at its centre, no dramatic tropical storms sweeping across it with satellite-worthy names. Instead, it rests quietly between the United States and Canada, bordered by cities, farmland and small towns. On a clear day, it can resemble an inland sea made for leisure. Boats move across it with confidence. Beachgoers step into its shallows without hesitation. The skyline of distant shores feels close enough to touch. And yet, more lives have been lost here than on any of its larger siblings. There is something quietly unsettling about that contrast. The most lethal of the Great Lakes is also the shallowest. The one that appears the most approachable has proven time and time again to be the least forgiving. It does not roar before it strikes. It does not advertise its danger. It simply changes. Before we go any further, I'd like you to consider something simple. Where are you listening from tonight? Are you near water, perhaps a coastline, a river, or a quiet pond? Or are you miles from any shore surrounded by streets and buildings instead of waves? And what time is it for you right now? Early evening when the sky begins to dim? Late at night when most of the world feels still? It's interesting how a single place, like a lake, can mean something entirely different depending on where and when we encounter it. If you find this exploration steady and grounding, if it gives you something to think about while the rest of the day fades into the background, I'd appreciate it if you liked the video and subscribed. It helps this calm corner of science reach others who might enjoy learning without urgency. Now, let's turn our focus fully to Lake Erie. Among the 5 Great Lakes, Erie is the smallest by volume and the second smallest by surface area. It stretches roughly 241 miles from west to east, with an average width of about 57 miles. On a map it looks substantial, but not overwhelming. Compared to Lake Superior, which plunges to depths over 1,300 feet, Erie seems modest. Its average depth is only about 62 feet. At its deepest point it reaches just 210 feet. That shallowness is not just a geographical detail. It is the key to understanding why this lake behaves the way it does. Water depth affects how a lake responds to wind, temperature and atmospheric pressure. Deep lakes absorb and distribute energy differently. They warm slowly, cool slowly, and their vast depths act as a kind of buffer. Shallow lakes, however, react quickly. When strong winds move across a shallow body of water, the energy transfers more directly. Waves build faster. The water becomes turbulent in a shorter period of time. What begins as a steady breeze can transform the lake's surface in minutes. This is one of Erie's defining characteristics. It changes quickly. Storm systems travelling across North America often move from west to east. Lake Erie's long east-west orientation means winds can sweep across the entire length of the lake without interruption. Meteorologists call this distance fetch. The longer the fetch, the more time wind has to build waves. On Lake Erie, that fetch can extend for hundreds of miles. Combine that with shallow depth, and the result is steep, closely spaced waves that rise rapidly and break hard. Unlike ocean swells, which are often long and rolling, Erie's waves tend to be short and aggressive. Boaters sometimes describe them as chaotic. One moment, the water seems manageable. The next, sharp peaks begin forming with little warning. Small vessels are especially vulnerable in these conditions. Even experienced sailors have been caught off guard. Historical records show that Lake Erie has claimed thousands of ships since the early days of European settlement. Commercial vessels, fishing boats, passenger steamers, and private crafts have all met the same fate. Some wrecks were caused by mechanical failure or navigational error. Many, however, were the direct result of sudden storms. In the 19th century, before modern forecasting, captains relied heavily on visual cues and barometric readings. A slight drop in pressure might hint at trouble, but there was no satellite imagery, no Doppler radar, no real-time alerts transmitted to handheld devices. Storms could develop and intensify with little notice. Crews often found themselves facing gale-force winds hours after setting out under clear skies. Even today, with advanced forecasting tools, Lake Erie remains unpredictable. Weather systems can intensify as they pass over the relatively warm surface of the lake, particularly in transitional seasons like autumn. Warm water meeting cold air creates instability. Instability fuels storms. Thunderstorms can form quickly, bringing lightning, heavy rain, and powerful gusts that churn the lake into a hazardous state. Then there are winter conditions. When cold Arctic air sweeps across the region, Erie's shallow water cools rapidly. Ice forms more quickly here than on the deeper Great Lakes. At first glance, ice might seem like a stabilising force, but it introduces its own risks. Expanding and shifting ice sheets can trap vessels. Sudden thaws can break apart what once appeared solid. For those who venture out onto frozen surfaces, misjudging thickness can be fatal. The human factor cannot be ignored either. Lake Erie is bordered by major population centres such as Cleveland, Buffalo, Toledo and Detroit. Millions of people live within driving distance of its shores. Accessibility increases usage. More boats, more swimmers, more recreational activity naturally lead to a higher number of incidents. In that sense, statistics are influenced not only by environmental danger but by exposure. Still, exposure alone does not account for everything. There is a psychological element to Erie's reputation. It does not inspire the same awe as Lake Superior, whose immense depth and frigid waters command respect almost instinctively. Erie feels manageable, familiar. It resembles an oversized version of lakes many people grew up around. That familiarity can reduce caution. A calm morning can encourage decisions that seem reasonable at the time. The horizon appears steady. The forecast looks acceptable. The engine sounds fine. And then conditions shift. Rescue operations on Lake Erie often describe scenarios where distress calls come in rapidly during sudden squalls. Winds increase beyond what smaller crafts can handle. Waves begin overtopping decks. In shallow areas, sandbars and submerged obstacles create additional hazards. Unlike the open ocean, where depth is vast and consistent, Erie's basin includes varying underwater terrain that can amplify wave action. Another contributing factor is water temperature. Even in summer, Lake Erie's water can be cold enough to trigger cold water shock. When someone unexpectedly falls into cold water, the body reacts immediately. Rapid breathing, involuntary gasping, and loss of muscle control can occur within seconds. Strong swimmers can become incapacitated quickly. Hypothermia may follow if rescue is delayed. It's easy to assume that danger requires dramatic visuals, towering waves, dark clouds filling the sky, but often it's the combination of moderate factors that proves most hazardous. A boat slightly overloaded, a life jacket left unsecured, a weather shift underestimated by half an hour. Lake Erie's danger tends to emerge from these accumulations rather than singular catastrophic events. Over the decades, improvements in navigation technology have reduced some risks. GPS systems provide accurate positioning. Marine radios allow instant communication. Weather alerts are more accessible than ever, and yet accidents continue. Not because technology has failed entirely, but because nature remains variable and human decision-making remains imperfect. It is also worth considering how Erie's ecosystem has influenced its history. Pollution and algal blooms have periodically affected water quality. While these issues are primarily environmental and health concerns, They also reflect the broader story of human interaction with the lake. Industry, agriculture, shipping, recreation, and urban development have all shaped its shoreline and waters. Increased traffic inevitably increases the chance of mishap. At the same time, Lake Erie is vital. It supports commercial shipping routes connecting the interior of North America to the Atlantic Ocean through the St. Lawrence Seaway. It provides drinking water to millions. It sustains fisheries and tourism economies. Its role is not defined solely by tragedy. It is a working lake, a living lake, and a heavily used one. When statistics label it the deadliest Great Lake, the term does not mean it is constantly violent. It means that over time, more recorded fatalities have occurred here than elsewhere in the system. That distinction matters. Danger is not a permanent state. It is a potential that emerges under specific conditions. Understanding those conditions requires looking closely at the lake's physical structure. Its three distinct basins, western, central, and eastern, behave differently. The western basin is the shallowest, averaging around 24 feet. It warms quickly in summer and freezes readily in winter. The central basin is deeper, while the eastern basin reaches the lake's maximum depth. Wind moving across these basins interacts with each differently, creating varied wave patterns and currents. One phenomenon particularly relevant to Lake Erie is the Seiche. A Seiche is a standing wave oscillation within an enclosed body of water, often triggered by sustained winds or sudden atmospheric pressure changes. When strong winds push water toward one end of the lake, water levels can rise significantly there while dropping at the opposite end. Once the wind subsides, the water sloshes back. This oscillation can continue for hours or even days. Water levels along shorelines can change rapidly, surprising those who assume stability. In some recorded events, Seiches have caused water level differences of several feet between opposite shores. Harbours have been temporarily drained. Boats have been left stranded. The water does not simply move up and down, it shifts laterally across vast distances. All of these elements combine to shape Lake Erie's personality. Shallow depth, long fetch, rapid weather changes, heavy human use, complex basin structure, oscillating water levels. None of these alone guarantees danger. Together, they create an environment that demands awareness, and that awareness is often learned through experience, sometimes at a high cost. Communities along Lake Erie carry stories passed down through generations. Sudden squalls that arrived without warning, fishing boats that failed to return, cargo ships that vanished beneath winter storms. These accounts form part of the region's collective memory. They serve as reminders that proximity does not equal safety. What makes Erie particularly interesting is how quickly its mood can shift within a single day. Morning calm can give way to afternoon turbulence. A stable forecast can evolve as air masses collide above warm water. The lake does not require dramatic atmospheric systems to become hazardous. Modest inputs can produce disproportionate outcomes. As we continue exploring this subject, it becomes clear that Lake Erie's reputation is not rooted in myth. It is built from measurable physical characteristics and documented history. To understand why it leads in fatalities among the Great Lakes, we need to examine how its geography shapes its behaviour in detail. Its shallowness, in particular, influences everything from wave formation to temperature fluctuation. So let's begin looking more closely at the lake's physical structure itself. Because once you understand how shallow water changes the rules of motion, the pattern behind many of Erie's most dangerous moments starts to make practical sense. If you've ever stood on the shore of Lake Erie on a quiet day, the first impression is usually one of ease. The horizon sits low and steady. The water often appears smooth, sometimes even glassy, reflecting the sky with very little distortion. There are days when the surface looks so calm that it barely seems capable of movement at all. People fish from piers, families walk along beaches, and small boats move without urgency. It is easy in those moments to assume the lake is predictable. That assumption has misled many people over the years. Lake Erie has a well-documented tendency to appear stable right up until it isn't. Unlike some coastal environments where incoming storms are visible far out at sea, conditions on Erie can change quickly and sometimes subtly. The sky may not darken dramatically at first. Winds can increase gradually enough to avoid immediate alarm, yet beneath that calm presentation, physical factors are already shifting. Air pressure drops, wind direction changes, temperature contrasts begin interacting with the water surface. By the time those changes become obvious visually, the lake may already be transitioning into rougher conditions. One major reason for this is its relatively shallow depth compared with other large lakes. Because the water column is not very deep, wind energy transfers efficiently into wave motion. There is less vertical space for energy to dissipate gradually. Instead, waves build faster and closer together. This produces what many boaters describe as steep chop rather than long rolling swells. Short, steep waves are harder to navigate, particularly for smaller recreational vessels. A calm morning on Lake Erie can therefore be misleading. Winds that increase only slightly can produce noticeable changes within an hour or two. The surface may still look manageable from shore while conditions farther out have already deteriorated. Distance plays tricks on perception. Waves that appear small from land can be several feet high once you're among them. Another factor contributing to Erie's deceptively calm appearance is its colour and clarity under certain conditions. On bright days with minimal wind, sunlight reflects evenly across the surface. Without large swells to cast shadows, the lake can resemble a flat expanse. Visual cues that would normally signal caution simply aren't present. This optical smoothness encourages activity. More boats go out, more swimmers enter the water. Increased activity naturally raises exposure to risk. Weather patterns around the lake also play a role. Lake Erie sits in a region where continental air masses frequently meet. Warm air from the south, cool air from the north, and moist air from the west can interact in complex ways. These interactions sometimes produce localized storms that develop quickly. Because the lake is long and oriented west to east, winds travelling along its length can accelerate without much interruption. Even moderate winds sustained over that distance can produce significant wave action. Then there is the issue of forecasting limitations. Meteorological technology has improved dramatically, but predicting exact timing and intensity of localized lake conditions remains challenging. Forecasts often describe general regional trends. Conditions on the water can deviate from those predictions due to small-scale atmospheric variations. Boaters who rely solely on broad forecasts may find themselves encountering stronger winds or higher waves than expected. Visibility changes add another layer. Fog formation on Lake Erie is common, especially during seasonal transitions when air temperature differs significantly from water temperature. Warm air moving over cooler water can produce dense fog quickly. Visibility may drop to near zero. Navigational hazards increase. Other vessels become difficult to detect. Shorelines disappear from view. Even experienced captains must rely heavily on instruments in such conditions. Fog also contributes to the lake's calm illusion. When the horizon fades and sound becomes muffled, the environment feels quiet and still. But fog does not mean stable water. Winds can still build waves beneath it. The sensory mismatch, calm atmosphere combined with the rough water can be disorienting. Historical accounts frequently mention this combination. Sailors reported departing under clear or lightly hazy skies, only to encounter thick fog and rising wind hours later. Before modern radar and GPS, such situations were particularly hazardous. Navigational errors increased, collisions occurred, ships sometimes ran aground simply because crews could not see shoreline features. Temperature fluctuations further complicate the picture. Because Erie warms quickly in summer due to its shallowness, it also cools quickly when colder air arrives. Rapid cooling can destabilize the atmosphere, contributing to sudden storm formation. Conversely, warm water can energize passing storm systems, intensifying them beyond initial expectations. This responsiveness to atmospheric change is part of what makes the lake dynamic. It reacts quickly. there is very little lag between environmental input and surface response. That responsiveness is scientifically interesting but operationally challenging. Human perception does not always keep pace with rapid environmental change. Many people rely on visual stability to judge safety. If the lake looks calm, it feels safe. If waves are not yet large, departure seems reasonable. But on Lake Erie, early conditions are not always reliable indicators of later ones. That disconnect between appearance and potential outcome is central to its reputation. Recreational boating statistics illustrate this point. A significant portion of incidents occur during periods initially described as fair weather. Conditions deteriorate after departure. Smaller vessels, particularly those without enclosed cabins or advanced navigation equipment, are more vulnerable. Wind-driven waves can swamp open boats quickly. Mechanical issues that would be minor on calm water become serious when waves increase. Swimming incidents follow similar patterns. On calm days, beaches attract large numbers of visitors. As winds shift, rip currents and longshore currents can strengthen. These currents are not always visible from shore. Swimmers may suddenly find themselves pulled sideways or away from the beach. Panic often follows, increasing fatigue and risk. Unlike ocean rip currents, which many coastal regions actively educate about, Great Lakes currents receive less public attention. Visitors unfamiliar with lake-specific hazards may underestimate them. Lake Erie's relatively gentle appearance reinforces that underestimation. Commercial shipping experiences the lake differently, but not necessarily more safely. Large cargo vessels are better equipped to handle rough conditions, yet even they must respect Erie's wave patterns. Steep, closely spaced waves place structural stress on hulls. Cargo shifting becomes a concern. Reduced visibility from fog or precipitation complicates navigation in busy shipping lanes. Seiches, mentioned earlier, also contribute to Erie's unpredictable nature. Sustained winds can push water toward one end of the lake, raising levels there while lowering them elsewhere. When the wind subsides, water oscillates back. Shorelines experience sudden level changes. Harbours can become temporarily shallow or unexpectedly flooded. These oscillations are not always widely understood outside maritime communities. For shoreline residents, the lake's calm appearance can foster a sense of permanence. Waterfront properties seem stable. Beaches appear consistent. But long-term observation shows variability. Storm surges, Seiches, and seasonal changes alter water levels. Infrastructure planning must account for these fluctuations even when daily conditions seem tranquil. Wildlife patterns also reflect the lake's variability. Fish distribution shifts with temperature gradients and oxygen levels, which change rapidly in shallow water. Bird migration routes sometimes adjust based on lake conditions. Ecologists studying Erie often emphasize its responsiveness, compared with deeper lakes. Pollution and nutrient runoff have historically affected Lake Erie more noticeably as well. Shallow water warms quickly, promoting algal growth under certain conditions. These blooms can change water colour dramatically, sometimes giving the surface a greenish tint. While primarily an environmental issue, such blooms also affect recreation, visibility, and water quality perception. Public awareness campaigns over recent decades have improved understanding of Erie's complexities. Boating safety courses, weather alert systems, and shoreline education initiatives all contribute to reducing incidents. Yet awareness must continually adapt because the lake itself remains variable. Technological aids have become increasingly common. Smartphone weather apps, marine band radios, AIS vessel tracking systems, and improved life-saving equipment all enhance safety. However, technology works best when paired with cautious judgment. Over-reliance can create complacency, particularly if devices fail or forecasts change unexpectedly. The idea that a lake can appear calm while harbouring potential instability is not unique to Erie, but its particular combination of shallow depth, orientation, and heavy use amplifies the effect. It is both accessible and dynamic, familiar yet complex. For many residents of the region, this dual nature becomes part of everyday awareness. They learn to read subtle cues, wind direction shifts, cloud formation patterns, temperature changes and water coloration. These observational skills often supplement formal forecasts. Visitors may not have that experiential knowledge. A weekend trip, a rented boat, or a spontaneous swim might occur without full appreciation of how quickly conditions can evolve. That difference between local familiarity and visitor perception sometimes appears in accident reports. Even seasoned mariners occasionally misjudge Erie. Confidence built from years of experience elsewhere does not always translate perfectly. Each large body of water has unique characteristics. Erie's shallowness and fetch create a specific wave signature that requires adjustment. Standing again at the shoreline on a quiet evening, it is easy to see why the lake invites approach. The surface reflects sunset colours. The air feels still. Distant boats move steadily. Nothing suggests imminent change, yet the same physical properties that produce that calm appearance can also enable rapid transformation when atmospheric conditions shift. Understanding that balance is less about fear and more about respect. A lake does not need to look threatening to require caution. Stability on the surface does not guarantee stability beneath or ahead in time. This principle applies not only to Lake Erie but to many natural systems. Still, Erie offers a particularly clear case study. As we continue exploring why it has earned its reputation among the Great Lakes, the next step involves looking closely at the specific geographical characteristics that shape its behaviour, especially the implications of being the shallowest in the system. When people first learn that Lake Erie is the shallowest of the Great Lakes, the reaction is often mild surprise rather than concern. Shallow water sounds less intimidating than deep water. Depth tends to be associated with danger in a very intuitive way. Oceans feel powerful because they are deep. Lake Superior carries a reputation partly because of its enormous volume and depth. By contrast, a lake that averages just over 60 feet deep can sound approachable, even gentle. Yet in Lake Erie's case, that relative shallowness is not a safety feature. It is one of the main reasons the lake behaves the way it does, and why its surface conditions can change so quickly. The geography of the lake, its shape, depth, shoreline configuration, and surrounding land all combine to create a system that responds rapidly to environmental input. The result is a body of water that rarely stays in one state for very long. To understand why depth matters so much, it helps to think about how wind transfers energy into water. When wind blows across a lake, it creates friction on the surface. That friction produces waves. In deeper water, some of that energy disperses downward. The vertical space allows the energy to spread out. Waves may grow larger over distance, but they tend to form longer swells with smoother spacing. In shallow water, there is less vertical room for energy distribution. The energy remains concentrated near the surface, leading to steeper, more abrupt waveforms. Lake Erie's average depth of about 62 feet is very shallow compared with the other Great Lakes. Lake Superior, for example, averages nearly 500 feet. Even Lake Ontario, often considered moderate among the five, averages more than 200 feet. This difference means that when wind moves across Erie, wave formation accelerates faster than on the deeper lakes. The lake simply does not have the buffering depth to absorb the energy gradually. This effect is most noticeable during sustained winds. Because Lake Erie stretches roughly west to east, prevailing weather systems travelling in that direction have a long uninterrupted path over water. Meteorologists refer to this uninterrupted distance as fetch. A long fetch allows wind to build wave energy progressively. On Erie, the fetch can extend across hundreds of miles. Combine that with shallow depth, and the result is waves that build quickly, often becoming steep and closely spaced. Those closely spaced waves create handling challenges for boats. Longer ocean swells rise and fall gradually. Steep lake waves can strike hulls more abruptly. The shorter interval between wave crests gives vessels less recovery time. Smaller boats may pitch and roll rapidly. Larger ships experience structural stress differently than they would in deeper water. Another geographical aspect influencing Lake Erie is its division into 3 distinct basins: the Western Basin, the Central Basin, and the Eastern Basin. Each has different average depths and characteristics. The Western Basin is the shallowest, averaging around 24 feet. It warms rapidly in spring and summer and freezes earlier in winter. The Central Basin is somewhat deeper, while the Eastern Basin contains the lake's deepest point at around 210 feet. These basins do not behave identically. Wind moving across them interacts differently depending on depth. The Western Basin, being very shallow, reacts almost immediately to strong winds. Wave height can increase rapidly. The Central Basin has slightly more moderating capacity. The Eastern Basin, though still shallow by Great Lakes standards, allows somewhat longer wave formation. When storms pass along the lake's length, conditions can vary dramatically from one basin to another. Water temperature patterns are also influenced by this basin structure. Shallow water warms faster because sunlight penetrates more effectively throughout the water column. During summer, the Western Basin can become relatively warm compared with deeper sections. Warm water can fuel atmospheric instability when cooler air passes overhead. That instability can contribute to storm development, sometimes intensifying weather systems that might otherwise remain moderate. In winter, the same shallow depth causes rapid cooling. Ice formation begins earlier in Erie than in the other Great Lakes. Ice cover can appear extensive, sometimes giving the impression that the lake is stable and dormant. However, ice introduces its own hazards. Wind can move ice sheets. Temperature fluctuations cause expansion and contraction. Cracks form. Pressure ridges develop. Navigation becomes complicated. Ice may appear solid from shore but remain thin or unstable farther out. Geography also influences water circulation. Lake Erie receives inflow primarily from the Detroit River at its western end and drains through the Niagara River in the east. This west-to-east flow aligns with prevailing winds. Water movement therefore combines natural outflow with wind-driven surface currents. Under strong winds, water can accumulate at one end of the lake. This leads to the Seiches phenomenon discussed earlier, where water levels oscillate across the lake. Seiches can produce rapid shoreline changes. Water levels may rise significantly at one end while falling at the other. When the wind subsides, the water sloshes back. Oscillation continues until equilibrium returns. Shoreline communities sometimes experience temporary flooding or unexpected low water levels. Harbours may become difficult to navigate. Boats can be left stranded or exposed. The shoreline itself contributes additional complexity. Lake Erie's northern and southern shores include a mix of urban development, wetlands, cliffs, beaches, and river mouths. Each feature influences local wind patterns and wave reflection. Bays and inlets can amplify wave energy under certain wind directions. Cliffs can funnel wind, increasing its speed locally. Wetlands may dampen some wave energy but also complicate navigation. Sandbars are another geographical feature that affects safety. Because the lake is shallow, sediment movement reshapes underwater terrain over time. Sandbars may form in areas previously clear. Charts help identify known hazards, but sediment shifts can occur between surveys. Boats operating in shallow regions must remain alert to changing depths. Visibility issues can also have geographical roots. Warm, shallow water interacting with cooler air produces fog, particularly in spring and early summer. Fog reduces visual navigation cues. Shoreline features disappear. Other vessels become difficult to detect. Radar and GPS mitigate some risk, but small recreational boats may lack advanced systems. Lake Erie's position within North America places it in a corridor where weather systems frequently pass. Storm tracks often follow west to east paths across the continent. The lake's orientation aligns with those tracks. Weather systems therefore interact with the lake directly, rather than glancing off at an angle. This alignment increases the frequency of strong wind events over the lake. Topography around the lake also matters. Relatively flat surrounding land allows winds to maintain speed as they approach the water. There are few major mountain barriers to disrupt airflow before it reaches the lake. As a result, wind energy arrives relatively intact, ready to interact with the water surface. Urban heat effects from nearby cities can subtly influence local atmospheric conditions as well. Temperature differences between urban areas and open water sometimes contribute to localized convection patterns. While these effects are typically modest, they can add complexity to already variable weather systems. The geographical setting also explains why Lake Erie supports such extensive human activity. Its relatively shallow depth historically made it attractive for fishing, transportation and settlement. Ports developed along its shores. Shipping routes connected inland resources to broader markets. Industrial growth followed. Today, the lake remains economically important, supporting commerce, recreation, and water supply. High usage increases exposure to geographical hazards. More vessels, more swimmers, more shoreline infrastructure all interact with the lake's physical characteristics. Incidents are therefore partly a function of geography and partly a function of human presence. Another geographical factor sometimes overlooked is the lake's sediment composition. Erie contains significant nutrient loads from agricultural runoff and river inflows. These nutrients contribute to algal blooms under favourable conditions. While primarily an environmental concern, blooms can reduce water clarity, affect oxygen levels, and alter ecosystem dynamics. Reduced visibility in water can complicate search and rescue operations. Oxygen depletion can impact fish populations, influencing fishing activity patterns. Depth variation within the lake also affects thermal stratification. In deeper lakes, distinct temperature layers form in summer. Erie's shallowness limits stratification in some areas, while allowing partial layering in others. This uneven stratification influences oxygen distribution, fish habitats, and water mixing. Strong storms can disrupt these layers quickly, bringing colder bottom water to the surface. Rapid mixing affects not only ecology but also surface conditions. Temperature changes influence air-water heat exchange, which can modify local weather patterns. Again, the lake responds quickly because of its limited depth. For those navigating the lake, charts showing bathymetry, underwater depth contours, are essential. Depth changes that might be gradual elsewhere can be abrupt here. Shoals and ridges create localized wave amplification. Waves steepen as they encounter shallower areas, increasing breaking intensity. This process is similar to how ocean waves break near beaches, but on Lake Erie, it can occur far from shore because the entire lake is relatively shallow. A vessel may be miles offshore yet still encounter bottom-influenced wave patterns. Understanding these geographical dynamics helps explain why Erie has earned its reputation. It is not simply a matter of storms being more frequent or more violent. It is about how the lake's physical characteristics interact with normal weather patterns to produce conditions that can escalate quickly. From above, on a map, Lake Erie appears straightforward. A broad oval of water bordered by populated land. But geography is not only about shape, it is about depth, orientation, surrounding terrain, sediment composition, basin structure, and hydrological connections. Each element contributes to behaviour. This behaviour does not mean the lake is constantly hazardous. Many days pass with calm water, safe navigation, and enjoyable recreation. The key point is variability. Geography makes Erie responsive. Responsive systems are dynamic. Dynamic systems require attention. As awareness grows, safety practices continue improving. Better charts, better forecasting, better education all reduce risk. Still, geography does not change quickly. The lake remains shallow, winds still travel long fetch distances, basins still interact differently. These fundamental characteristics persist. With that geographical foundation in mind, it becomes easier to understand why certain weather patterns have such pronounced effects here, particularly how storms can develop and intensify with surprising speed once atmospheric conditions begin shifting over the lake. If you spend enough time around Lake Erie, you begin to hear a particular kind of story repeated in different ways. Someone heads out under a bright sky, the forecast looks acceptable, winds seem manageable. Then, sometime later, sometimes within the same afternoon, conditions begin to change. The air cools unexpectedly, clouds thicken, the horizon becomes less distinct, waves that were barely noticeable earlier start rising faster than expected. Within a short span of time, what looked like a calm outing turns into a situation requiring serious attention. These sudden shifts are not random. They are tied to how weather systems interact with large bodies of water, and Lake Erie's specific geography makes those interactions especially responsive. Its shallow depth, its orientation along common storm tracks, and the temperature behaviour of its water all contribute to storm development that can feel abrupt, even though the underlying processes follow consistent physical principles. To begin understanding this, it helps to look at how air masses move across North America. Broadly speaking, weather in the region surrounding Lake Erie is influenced by continental air from the north, maritime air from the south and east, and occasionally dry air from the west. These air masses differ in temperature, moisture content, and density. When they meet, boundaries form. Meteorologists call these boundaries fronts. A cold front occurs when cooler, denser air pushes beneath warmer air. The warmer air is forced upward, and as it rises it cools. Cooling air loses its ability to hold moisture, leading to condensation. Clouds form. If the upward motion is strong enough, thunderstorms can develop. A warm front involves warmer air gradually sliding over cooler air, producing different cloud structures and often steadier precipitation. Lake Erie plays a role in both scenarios. Because its water temperature often differs from surrounding land temperatures, especially during seasonal transitions, it modifies the air passing over it. In spring, the lake is usually colder than the land. Air moving over it cools. In autumn, the lake often remains warmer than the cooling land. Air passing over it warms and picks up moisture. These exchanges can strengthen existing weather systems or contribute to new ones forming. One important factor is evaporation. When relatively warm lake water meets cooler air, evaporation increases. Moisture enters the lower atmosphere. Moist air is less dense than dry air and can rise more readily when lifted by frontal systems or surface heating. This rising moist air fuels cloud development and precipitation. If atmospheric instability is present, thunderstorms can grow quickly. Because Lake Erie is shallow, its surface temperature changes faster than deeper lakes. That responsiveness means the lake can shift from being a cooling influence to a warming influence relatively quickly within a season. Rapid temperature adjustment contributes to dynamic air-water interactions. Wind patterns also play a central role. Prevailing winds often follow a west-to-east trajectory across the region. Lake Erie's long axis aligns with that direction. Winds crossing the full length of the lake can pick up moisture and energy over hundreds of miles of open water. By the time they reach the eastern end, they may carry significantly more energy than when they began. This process is well known in winter as lake effect snow. Cold air moving over relatively warm lake water picks up moisture and heat. As that air reaches land, it cools again, releasing moisture as snow. But similar energy exchanges occur year-round, not just in winter. In warmer months, the same mechanisms can intensify thunderstorms rather than snowfall. Thunderstorms over Lake Erie can develop quickly because the lake provides both moisture and temperature contrast. Warm water releases latent heat through evaporation. Rising moist air condenses into clouds, releasing additional heat that fuels further upward motion. This positive feedback can produce rapid storm intensification. Lightning becomes a hazard in such storms. Open water offers little shelter. Boats are often the highest conductive objects on the surface. Metal masts, fishing equipment, and communication antennas increase strike risk. Even when lightning does not strike directly, Nearby strikes can cause electrical surges affecting onboard electronics. Wind shifts associated with thunderstorms are another concern. Gust fronts, sudden outflows of cooler air from a storm cell, can produce sharp increases in wind speed. These gusts may arrive before heavy rain begins, catching boaters off guard. Waves respond quickly to these gusts, especially given the lake's shallow depth. Rainfall itself affects visibility and surface conditions. Heavy rain reduces sight distance. Navigation markers become harder to see. Other vessels may disappear behind precipitation curtains. Combined with wind-driven waves, this reduction in visibility complicates safe manoeuvring. Barometric pressure changes provide early indicators of storm development, but not everyone monitors them closely. A falling barometer signals approaching instability. Historically, mariners relied heavily on barometric readings. Modern recreational users sometimes rely more on visual cues, which may lag behind atmospheric changes. Another scientific aspect involves atmospheric instability. Instability occurs when warm air near the surface lies beneath cooler air aloft. Warm air wants to rise. If moisture is present, rising air condenses into clouds. Strong instability can produce towering cumulonimbus clouds associated with thunderstorms. Lake Erie can contribute to this instability by warming the air directly above it, or by adding moisture that enhances buoyancy. Wind shear also influences storm behaviour. Shear refers to changes in wind speed or direction with height. Adequate shear can organise thunderstorms into more persistent systems. Organised storms tend to last longer and produce stronger winds than isolated cells. Over Lake Erie, interactions between land breezes, lake breezes, and larger-scale atmospheric flows can create localized shear zones. Lake breezes deserve particular attention. During sunny days, land warms faster than water. Warm air over land rises, drawing cooler air inland from the lake. This creates a lake breeze circulation. Later in the evening, the pattern can reverse as land cools faster than water. These local wind shifts sometimes interact with larger weather systems, contributing to storm initiation. For people on the water, these breezes may feel mild initially, but when combined with frontal boundaries or atmospheric instability, they can become part of more significant wind events. Predicting exactly how local breezes will interact with regional weather systems remains complex. Storm speed is another factor. Some systems move quickly across the lake. Rapid movement reduces preparation time. A storm visible on the western horizon might reach the central basin sooner than expected. Conversely, slow-moving systems can linger, producing prolonged wind and wave activity. Satellite imagery and Doppler radar have improved storm monitoring dramatically. Weather services issue marine forecasts and warnings. Many boaters carry weather radios or smartphone apps providing alerts. Still, interpreting forecasts requires understanding probabilities rather than certainties. Forecasts describe likely scenarios, not guarantees. Temperature gradients within the lake itself also influence storm interaction. Surface water may differ in temperature across basins due to depth variation and inflow patterns. These gradients affect evaporation rates and local atmospheric stability. Storms passing over warmer sections may intensify, compared with those over cooler sections. Another phenomenon sometimes observed is waterspouts. Waterspouts resemble tornadoes forming over water. They occur when rotating air columns interact with warm water surfaces. Lake Erie occasionally experiences waterspouts, particularly during late summer and early autumn, when water temperatures remain relatively warm while cooler air masses arrive. While most waterspouts are weaker than tornadoes, they still pose hazards to vessels. Visibility reduction during storms extends beyond rain. Spray from breaking waves can create mist, reducing clarity. Combined with low cloud ceilings, this can produce conditions where horizon lines disappear. Spatial orientation becomes challenging. Navigation instruments become essential. Sound also changes during storms. Wind and wave noise increase. Engine sounds may become harder to distinguish. Verbal communication aboard vessels becomes more difficult. These sensory changes add to operational complexity. Storm aftermath can present additional challenges. Debris washed into the water, altered sediment patterns, and temporary navigation marker displacement sometimes follow strong storms. Even after skies clear, conditions may remain unsettled. From a scientific standpoint, none of this behaviour is mysterious. It reflects well-understood atmospheric physics. Warm and cold air interactions, moisture exchange, energy transfer, and fluid dynamics all operate predictably in principle. What creates difficulty is the scale and variability of real-world conditions. Small changes in initial variables can produce noticeable differences in outcomes. Lake Erie's characteristics amplify responsiveness. Shallow depth allows rapid thermal change. Long fetch allows wind energy build-up. Geographic position exposes it to frequent air mass interactions. High human usage increases the number of people affected by sudden changes. Understanding these mechanisms helps explain why experienced mariners emphasize preparation even when conditions look calm. Safety equipment, communication devices, and contingency planning become important not because storms are constant, but because they can develop faster than expected. It also explains why historical accounts often mention surprise. Before modern forecasting, sudden storms seemed almost unpredictable. Today, forecasting skill has improved, but local variability still produces surprises. This responsiveness to atmospheric change links directly to how waves behave once winds increase. The science of wave formation on shallow water reveals why Lake Erie's waves can become steep and hazardous, faster than many people anticipate. If there is one feature of Lake Erie that has surprised more sailors than any other, it is not the wind itself, but what the wind does to the water. The air may begin moving at a speed that feels manageable. Flags flutter more firmly, the surface ripples. Nothing appears extreme. And then, within a relatively short span of time, the water transforms. Waves do not simply grow taller, they grow sharper, closer together, more forceful in the way they strike a hull. To understand why this happens, it helps to look closely at how waves form in the first place. Wind blowing across water transfers energy through friction. At first, small ripples appear. As wind continues, those ripples increase surface roughness, allowing more energy transfer. Over time, wave height increases. The amount of growth depends on three primary factors: wind speed, wind duration, and fetch, the uninterrupted distance over which wind blows. Lake Erie has a long fetch along its west to east axis. When strong winds align with that axis, they can move across nearly the entire length of the lake. This allows waves to build progressively. But fetch alone does not explain Erie's distinct wave character. Depth plays a crucial role. In deep water, waves have space to develop longer wavelengths. The distance between successive crests grows as wave energy spreads vertically and horizontally. In shallow water, however, waves begin interacting with the lakebed more quickly. This interaction alters their shape. As waves approach shallower depths, their speed decreases because the bottom interferes with orbital water motion beneath the surface. When wave speed decreases but energy remains, the wave height increases and the wavelength shortens. The result is a steeper wave. Lake Erie's average depth of about 62 feet means that even offshore, many waves are influenced by the bottom sooner than they would be in deeper lakes or oceans. When winds intensify, waves do not have the luxury of spreading out into long rolling swells. Instead, they compress vertically and horizontally. Crests become sharper. The face of the wave steepens. Breaking occurs more readily. For a sailor, this difference is significant. Long swells allow a vessel to rise and fall gradually. Steep, short-period waves cause more abrupt motion. A boat climbing one crest may immediately descend into the next trough with little recovery time. This repetitive pitching can strain both vessel and crew. Wave period, the time between successive crests passing a fixed point, is particularly important. On Lake Erie, wave periods can be shorter than on deeper bodies of water under similar wind speeds. Short periods mean waves arrive more frequently. For smaller recreational boats, this frequency increases the risk of taking water over the bow or stern. There is also the matter of wave direction relative to vessel orientation. When waves approach directly from ahead, a boat may pound heavily. When they strike from the side, rolling becomes more pronounced. Steep side waves can destabilize smaller crafts quickly. Experienced operators adjust speed and heading accordingly, but sudden wind shifts can change wave direction unexpectedly. Wind gusts further complicate matters. Sustained wind builds wave structure, but gusts add bursts of energy that steepen existing waves. On Lake Erie, gust fronts from passing thunderstorms can rapidly increase wind speed. Waves that were manageable moments earlier may double in height within a short interval. Another aspect often underestimated is wave reflection. When waves strike shorelines, breakwaters, or harbour walls, they reflect back into the lake. Reflected waves interact with incoming waves, creating confused sea states. Interference patterns produce irregular peaks. Instead of predictable wave trains, sailors encounter chaotic surfaces with intersecting crests. Steering through such conditions demands attention and experience. The western basin of Lake Erie presents unique wave challenges. Its shallow depth allows bottom interaction almost everywhere. Waves there tend to be especially steep. Because the basin is narrower, reflected energy from shorelines can return quickly, adding complexity to wave patterns. In the central and eastern basins, depth increases somewhat, but still remains modest compared with other Great Lakes. When strong west winds blow, waves can build progressively across these basins. By the time they reach the eastern end, energy accumulation may produce some of the lake's highest waves. Reports of waves exceeding 10 feet are not uncommon during severe storms. While 10-foot waves on the ocean may not be extraordinary, on Lake Erie they behave differently. The shorter wavelength means that 10 feet of height may be packed into a tighter horizontal space. The angle of ascent becomes steeper. Breaking crests can occur more suddenly. Breaking waves introduce additional hazards. When a wave breaks, it releases kinetic energy forward and downward. This force can swamp small boats, damage equipment, and injure occupants. Even larger vessels must navigate breaking seas carefully to avoid structural stress. Commercial ships have historically reported heavy pounding on Lake Erie during storms. Cargo shifts can occur if waves strike repeatedly from similar angles. Modern ships are built to withstand such forces, but smaller vessels remain vulnerable. Another scientific principle relevant here is wave grouping. Waves often travel in sets rather than uniform sequences. A group may include several larger waves followed by smaller ones. Boaters who interpret a lull as improvement may be caught off guard by the next large set. On Lake Erie, rapid energy transfer and variable wind patterns can produce irregular groupings. Wind duration also affects wave growth. A brief gust may create temporary chop, but sustained winds allow full development. Because regional weather systems frequently move west to east across Erie, winds can align with the lake's axis for extended periods. Hours of sustained wind produce mature wave fields that require time to subside even after wind decreases. Residual wave energy lingers. A storm passing through may leave waves continuing long after skies clear. Boaters venturing out shortly after a storm sometimes encounter rough conditions despite calm air. Seiches influence wave behaviour as well. Oscillating water levels alter local depth temporarily. In shallower areas, even slight reductions in water level increase bottom interaction. Waves steepen more quickly over temporarily lowered water. Conversely, higher water levels may allow slightly longer wave formation. Temperature gradients across the lake can modify wind strength at the surface. Warm water heating overlying air may enhance mixing, bringing stronger winds from aloft down to the surface. This vertical mixing can increase surface wind speed beyond initial forecasts, amplifying wave growth. For sailors accustomed to ocean conditions, Erie's waves can feel unfamiliar. Ocean swells often roll in with rhythm. Lake Erie's chop feels more abrupt and less forgiving. reaction time decreases, equipment rattles more intensely, crew fatigue sets in sooner due to constant jarring motion. Smaller recreational boats, especially those under 25 feet, face greater risk. Freeboard height, the distance from waterline to deck edge, determines how easily waves can enter the boat. Steep waves striking the bow can send spray or water over the front. Repeated impacts increase the likelihood of swamping. Kayakers and paddleboarders are particularly exposed. Human-powered craft lack the speed to outrun deteriorating conditions. Once waves build, maintaining direction becomes physically demanding. Capsizing risk increases rapidly. Fishing boats operating farther offshore may experience delayed recognition of wave growth. Focused on equipment or catch, operators might not notice gradual increases until waves reach uncomfortable size. Returning to shore against building waves can become challenging. Marinas and harbours provide refuge, but entering them during rough conditions requires skill. Narrow channels with breaking waves on either side can amplify danger. Wave reflection inside harbour walls sometimes creates unexpected turbulence. From a physics perspective, none of these wave behaviours violate known principles. Wind transfers energy, shallow depth alters wave shape, fetch determines growth potential. What makes Lake Erie notable is how efficiently these factors combine. Moderate winds that might produce manageable swells elsewhere can create sharper, more chaotic seas here. Historical records of shipwrecks often mention heavy seas rather than extreme winds alone. Vessels may have been structurally sound, crews experienced, yet repeated wave impacts overwhelmed them. In earlier centuries, wooden hulls and less advanced navigation made survival even more difficult. Modern forecasting provides wave height predictions alongside wind speed. Yet interpreting those predictions requires understanding that wave character matters as much as height. A forecast of 4-foot waves with short periods may present more handling difficulty than 6-foot waves with longer spacing. As we continue examining why Lake Erie has accumulated its reputation, it becomes clear that wave behaviour is central, but waves are only part of the equation. Beneath the surface lies a long history of vessels that failed to overcome these conditions, leaving behind physical reminders of the lake's capacity to challenge even prepared crews. If you could drain Lake Erie completely and walk across its exposed basin, you would not find a smooth, empty floor of sand and stone. You would find wood and iron, broken hulls, scattered cargo, ribs of schooners rising from sediment, boilers from steamships resting at angles that no shipbuilder ever intended. The lakebed holds the physical record of centuries of navigation, commerce, optimism, and miscalculation. It is one of the clearest measures of how often this body of water has turned from cooperative to unforgiving. Estimates vary, but historians generally agree that Lake Erie has claimed thousands of vessels since European ships first began moving across its surface in the late 18th and early 19th centuries. Some of those losses were small fishing boats that left little documentation. Others were large commercial ships carrying grain, lumber, coal, iron ore, or passengers. Each wreck has its own story, but when viewed collectively, patterns emerge. Storms appear again and again in the records. Sudden wind shifts, rapid wave growth, reduced visibility, structural failure under repeated wave impact. In the early days of navigation on Lake Erie, vessels were primarily wooden sailing ships. Schooners and brigs relied entirely on wind for propulsion. When storms developed, crews had limited options. They could attempt to shorten sail, change heading, or seek shelter if a harbour was nearby. But harbours were not evenly distributed along the shoreline, and as we have already explored, storms could intensify quickly over the lake's shallow surface. One of the earliest large-scale naval engagements on the lake, the Battle of Lake Erie during the War of 1812, demonstrated that even military vessels were subject to the lake's volatility. Although that battle was fought intentionally, it occurred within the same environmental context that would later challenge commercial shipping. Wooden ships operating in confined basins face shifting winds and wave conditions that affected manoeuvrability. As trade expanded during the 19th century, Lake Erie became a critical link in North America's transportation network. Grain from the Midwest, coal from Pennsylvania, and timber from surrounding regions moved across the lake toward canals and rail connections. Ship traffic increased steadily. With increased traffic came increased exposure to weather risk. The 19th century lacked modern forecasting. Captains relied on experience, observation, and barometers. A falling barometer signalled trouble, but it did not specify timing or severity. Many vessels departed under clear skies only to encounter gales hours later. When west winds strengthened along the lake's long fetch, waves built quickly. Wooden hulls pounded repeatedly. Caulking loosened. Water seeped in. Pumps worked continuously, sometimes unsuccessfully. Records from major storm events describe dozens of ships lost in a single system. One notorious storm in October 1880, often referred to in maritime histories as one of the Great Lakes' most destructive events, caused widespread damage across multiple lakes. On Lake Erie, vessels were driven ashore, sunk offshore, or collided in reduced visibility. Crews struggled against wind and wave forces amplified by the lake's shallow geometry. Steam power eventually replaced reliance on sail alone. Steamships provided greater control over direction and speed. They could attempt to power through adverse conditions rather than being entirely at the mercy of wind direction. However, steamships were not immune to wave impact. Boilers and engines added weight and complexity. Structural integrity remained vulnerable to repeated pounding in steep seas. One factor contributing to Erie's high wreck count is its role as a connector between upper Great Lakes and the Atlantic via the Niagara River and later the Welland Canal system. Ships passing between lakes often transited Erie. High traffic density increased collision risk during fog or storms. Navigation markers in earlier centuries were fewer and less reliable. Lighthouses provided guidance, but visibility could vanish quickly in dense fog. Fog-related wrecks are common in Erie's history. Warm air passing over cooler water produces thick fog banks. Ships navigating without modern radar relied on visual cues and sound signals. Collisions between vessels or groundings on shoals occurred when those cues failed. Even experienced captains could misjudge distance or bearing when landmarks disappeared. The lake's shallow areas also created grounding hazards. Sandbars and shoals shift gradually over time due to sediment movement. Charts in earlier periods were less precise. A vessel slightly off course might strike bottom unexpectedly. In rough seas, grounding often led to hull breach and eventual sinking. Winter added another dimension. Although most navigation historically occurred outside the ice season, transitional periods in late autumn were particularly dangerous. Storm frequency increases during seasonal change. Cold air masses sweep across still warm water. Intense low-pressure systems develop. Ice formation may begin along edges, complicating manoeuvrability. One tragic example frequently cited in Lake Erie's maritime history is the loss of the passenger steamer Atlantic in 1852. Although the sinking occurred near Long Point in Canadian waters, it underscores the vulnerability of even large passenger vessels. The Atlantic collided with another ship in darkness and rough conditions. Hundreds of passengers perished. While collision was the immediate cause, limited visibility and navigational challenges played significant roles. Over time, advances in shipbuilding improved safety. Iron and later steel hulls replaced wood. Compartmentalization reduced flooding risk. Better pumps, radios, and signaling systems enhanced emergency response. Yet despite these improvements, Lake Erie continued to claim vessels. The 20th century saw continued losses, though fewer proportionally compared with earlier centuries. Mechanical failure sometimes compounded weather challenges. Engine trouble in calm conditions might be manageable. In rising seas, it became life-threatening. Without propulsion, a vessel loses the ability to maintain favourable orientation to waves. Modern divers have explored many of Erie's wrecks. Cold fresh water preserves hull structures better than saltwater environments. Some wrecks remain remarkably intact, resting upright on the lakebed. Others are scattered debris fields. Each site provides clues about the final moments of the vessel. Broken masts, torn hull plates, cargo spilled across sediment. Shipwrecks serve as underwater time capsules. They also remind current mariners that the lake's behaviour has not fundamentally changed, even if technology has. Wind still builds waves, fog still reduces visibility, storm systems still travel west to east. The distribution of wrecks across the lake reflects geographical patterns. Many lie in the eastern basin, where wave energy accumulates after travelling the full fetch. Others cluster near harbour entrances where vessels attempted to seek shelter during deteriorating conditions. Some rest in shallower western waters where sudden storms overwhelm smaller craft. Search and rescue operations historically faced immense difficulty. Without rapid communication, distress calls might not reach shore in time. Even if help launched quickly, steep waves and poor visibility hampered response. Survival time in cold water was limited. Life jackets were not universally worn or even available in earlier eras. The human toll associated with Erie's shipwreck history contributes significantly to its reputation as the deadliest Great Lake. Fatality counts over centuries accumulate. While modern safety measures have reduced large-scale losses, earlier centuries saw numerous events with dozens or even hundreds of casualties. It's important to note that not all wrecks resulted solely from storms. Human error, overloading, poor maintenance, and navigational misjudgment all played roles. But environmental conditions often amplified those human factors. A minor mistake in calm weather might be corrected. In rising seas, it became catastrophic. The lakebed today remains a protected archaeological resource in many jurisdictions. Divers must follow regulations when exploring wreck sites. Preservation efforts aim to maintain historical integrity while allowing controlled access for study. These submerged vessels provide tangible evidence of the lake's long relationship with human enterprise. For coastal communities, stories of shipwrecks are part of regional identity. Museums display recovered artifacts. Plaques mark shoreline burial sites. Local lore includes tales of ghost ships and unexplained lights, reflecting how deeply maritime loss resonates culturally. Yet beyond folklore lies measurable reality. Thousands of documented incidents, many directly linked to storm events and steep wave action, underline how geography and weather combine on Lake Erie. Its shallow depth accelerates wave growth. Its orientation aligns with prevailing winds. Its heavy traffic increases exposure. Modern shipping is far safer than in the 19th century. Real-time weather data, advanced hull design, satellite navigation, and coordinated rescue networks all reduce risk. Even so, the lake's fundamental physics remain unchanged. Looking down into Erie's waters, one sees not just relics but lessons. Each wreck represents a moment when conditions exceeded preparation, or when small errors met amplified environmental forces. Studying these histories helps explain not only past tragedies, but ongoing caution. Because while many vessels now cross Lake Erie safely each year, the same mechanisms that sank wooden schooners and early steamers continue operating beneath the surface. And beyond shipwrecks, other factors such as reduced visibility and atmospheric conditions still challenge modern navigation in ways that connect directly to the lake's enduring record. If you ask experienced mariners what unsettles them most on Lake Erie, many will mention not the waves, not even the storms themselves, but the moments when visibility simply disappears. The lake has a way of slipping into fog quietly. 1 hour the shoreline is visible, boats are easy to track, navigation markers stand out clearly. Then the horizon softens, contrast fades, and before long the entire scene becomes muted and indistinct. Sound carries differently. Distances become difficult to judge. Orientation relies less on sight and more on instruments. Fog on Lake Erie is not unusual. In fact, it is a predictable outcome of how temperature, moisture, and air movement interact around shallow water. Understanding how it forms helps explain why it can arrive quickly and linger long enough to complicate navigation. The most common type affecting the lake is advection fog. This forms when warm, moist air moves across cooler water. The air cools from below. Cooling reduces the air's capacity to hold water vapour, so condensation occurs. Tiny droplets form and remain suspended, creating fog. Because Lake Erie often remains cooler than surrounding land in spring and early summer, warm air flowing over it produces frequent fog banks. Radiation fog can also occur, especially during calm nights when land surfaces cool rapidly. Air near the surface cools with them. Moisture condenses and fog develops. Near shorelines, this type of fog may extend over the lake, particularly in sheltered bays. Steam fog, sometimes called sea smoke, appears when very cold air passes over relatively warm water. The lake evaporates moisture into the cold air, which then condenses visibly. This type is more common in late autumn and early winter. It often looks dramatic, with wisps rising from the surface, but it also reduces visibility significantly. Lake Erie's shallowness contributes to fog frequency, because water temperature changes relatively quickly. Temperature contrasts between water and air therefore arise often. Rapid warming in spring or lingering warmth in autumn both support fog formation. Visibility reduction on open water carries specific navigational consequences. Landmarks disappear first. Shorelines that normally provide orientation fade into uniform grey. Without visual references, estimating distance becomes challenging. A vessel that appears close may be farther away than expected, or vice versa. Navigation buoys and markers become difficult to spot. Even when painted in bright colours, their visibility depends on contrast with the background. Fog reduces contrast. Lights help at night, but during daytime fog, visual detection relies heavily on proximity. Sound signals historically played a larger role before electronic navigation became widespread. Foghorns, bells and whistles alerted nearby vessels to each other's presence. Today, sound signals remain important, especially for smaller craft without advanced radar. However, interpreting sound direction in fog is not straightforward. Sound refracts in moist air. Echoes from the water surface and shoreline can distort perception. Radar technology significantly improves safety. Radar detects objects by reflecting radio waves. Ships, buoys, shore structures, and even weather systems can appear on radar screens. Yet radar interpretation requires training. Small recreational boats may lack radar altogether. Those that have it may not use it frequently enough to build familiarity. Global positioning system navigation has also changed how mariners handle reduced visibility. GPS provides precise location data regardless of visibility. Chart plotters display vessel position relative to known hazards. Still, GPS does not show every obstacle, particularly floating debris or uncharted shoals. Automatic identification systems used by many commercial vessels transmit location and movement data between ships. This helps avoid collisions in low visibility. Recreational craft increasingly adopt simplified AIS receivers, but adoption is not universal. Fog increases collision risk primarily because reaction time decreases. When two vessels approach each other, visual detection usually provides early warning. In fog, detection may occur only when vessels are already close. Even moderate speeds can become hazardous. Lake Erie's shipping lanes carry commercial traffic regularly. Large freighters have limited maneuverability compared with smaller boats. Their stopping distance is substantial. When visibility drops, both commercial and recreational operators must adjust speed and maintain heightened awareness. Fishing vessels face additional challenges. Nets, lines, and gear deployed in the water create entanglement risks. Fog complicates monitoring of gear locations relative to other vessels. Radio communication becomes essential. Another visibility factor is precipitation. Rain often accompanies weather systems that already produce fog. Combined effects reduce clarity further. Spray from breaking waves adds another layer. Moisture on windshields and instrument screens interferes with visibility inside vessels as well. At night, fog interacts with artificial lighting in ways that can hinder rather than help. Bright lights reflect off water droplets, creating glare. Reduced forward visibility sometimes results when deck lights are too intense. Mariners often dim lights to improve contrast. Temperature gradients also influence how long fog persists. If wind increases slightly, fog may dissipate as mixing occurs, but calm conditions allow it to linger for hours. Lake Erie's sheltered bays and shallow western basin sometimes hold fog longer than open central areas. Seasonal timing matters. Spring sees frequent fog due to warm air moving over cold water. Autumn brings steam fog when cold air meets residual lake warmth. Summer thunderstorms may produce localized fog following rainfall as evaporation increases humidity near the surface. Psychological effects of reduced visibility deserve attention too. Humans rely heavily on vision for spatial orientation. When visual cues disappear, anxiety can increase. Decision-making may be affected. Maintaining composure becomes part of safe navigation. Experienced mariners develop habits to manage fog. Speed reduction is primary. Sound signals are used regularly. Communication channels remain open. Navigation lights are checked. Instrument monitoring becomes continuous rather than occasional. Training emphasizes redundancy. Visual navigation, electronic navigation, and auditory cues complement each other. If one fails, others remain available. Redundancy reduces reliance on any single system. Historical shipwreck records frequently cite fog as a contributing factor. Collisions between vessels occurred when each was unaware of the other until too late. Groundings happened when shoreline distance was misjudged. Some ships entered harbours off course due to poor visibility striking breakwaters. Before GPS, dead reckoning navigation required estimating speed, direction, and elapsed time. Small errors accumulated. Fog removed visual confirmation. Modern technology reduces but does not eliminate such risks. Search and rescue operations during fog face additional complexity. Locating distressed vessels becomes harder. Visual spotting from aircraft may be impossible. Radio triangulation and GPS distress signals improve response but depend on functioning equipment. Recreational users sometimes underestimate fog risk. A calm surface combined with reduced visibility can create a misleading sense of safety. Without waves, conditions feel manageable, yet collision risk remains. Disorientation can lead to navigation errors. Shoreline residents observe fog as part of normal seasonal cycles. Morning fog burning off by midday is common. From land, the lake may appear tranquil beneath a fog layer. Out on the water, the experience differs significantly. Environmental monitoring programs track fog occurrence because it affects shipping efficiency, aviation near coastal airports, and ecological conditions. Fog influences sunlight penetration into water, affecting photosynthesis and temperature regulation. Scientific measurement of visibility uses instruments like transmissometers and ceilometers. These provide objective data rather than relying solely on human observation. Data contribute to forecasting models that predict fog likelihood. Forecasting fog remains challenging because it depends on small-scale temperature and humidity variations. Models have improved but still carry uncertainty. Mariners treat fog advisories seriously even when forecasts are probabilistic. Safety education increasingly emphasizes preparedness rather than avoidance alone. Fog cannot always be predicted precisely. Having navigation equipment ready, understanding how to use it, and planning routes with safe margins all reduce risk. Lake Erie's history shows that visibility challenges interact with other hazards. Waves, storms, and currents become more dangerous when operators cannot see clearly. Fog rarely acts alone as a hazard. It amplifies existing ones. As navigation continues evolving with better technology, awareness remains central. The lake's shallow geography promotes rapid temperature change. Rapid temperature change promotes fog. Fog reduces visibility. Reduced visibility affects navigation decisions. And beyond visibility, the temperature of the water itself introduces another dimension of risk, particularly when unexpected immersion occurs, something that has shaped many incidents on the lake over time. When most people think about danger on Lake Erie, they picture storms, high waves, or perhaps fog rolling across the surface. What they rarely picture is the moment someone unexpectedly enters the water. A slip on a wet deck, a sudden lurch as a wave hits, a capsized kayak, a fall from a dock. In calm weather, such an event might seem manageable. The shoreline may be visible, rescue might feel immediate, but the water itself introduces a physiological hazard that is often underestimated, especially outside the peak of summer. Lake Erie, despite being the warmest of the Great Lakes during midsummer, remains cold for much of the year. Its shallowness allows it to warm quickly, but it also cools rapidly in spring and autumn. Even when air temperatures feel comfortable, water temperatures can lag behind. A sunny April afternoon might invite boaters out for the season's first trip, yet surface water temperatures may still hover near 40 degrees Fahrenheit. At that temperature, cold water shock becomes a serious threat within seconds. Cold water shock is not the same as hypothermia, though the two are related. Hypothermia develops over time as the body loses heat faster than it can generate it. Cold water shock happens immediately upon immersion in cold water. The body's response is involuntary and rapid. When cold water contacts the skin, especially the torso, nerve endings send intense signals to the brain. The initial reaction is a sudden gasp reflex. Breathing rate increases sharply. Heart rate spikes. Blood pressure rises. If a person's head is underwater at the moment of that involuntary gasp, water may be inhaled. Even if the head remains above water, rapid breathing can lead to hyperventilation. Hyperventilation reduces carbon dioxide levels in the blood, causing dizziness and disorientation. Within seconds, an otherwise strong swimmer may feel out of control. Lake Erie's temperature profile creates extended periods when this risk is present. In early spring, the lake may still be near its winter minimum. Ice may have recently melted, but water temperature remains dangerously low. Late autumn presents similar conditions. Air temperatures may still feel moderate, but cooling water increases risk. The western basin, being shallowest, warms first in summer. By July and August, surface temperatures may reach the upper 70s Fahrenheit. During that period, cold water shock risk decreases. However, outside that narrow window, immersion remains hazardous. Boaters in May, September or October often encounter water temperatures low enough to trigger shock. Seasonal transitions also bring more frequent storms. As discussed earlier, autumn sees increased storm activity due to temperature contrasts between water and incoming cold air masses. These storms increase the likelihood of falling overboard. Combined with cold water, risk multiplies. Cold water shock typically unfolds in stages. The first stage, lasting about 1 minute, is the initial gasp and breathing disruption. The second stage, lasting up to 10 minutes, involves rapid cooling of muscles and reduced coordination. Fine motor skills deteriorate, swimming becomes less efficient. Grip strength weakens. The third stage, occurring over longer periods, is hypothermia, where core body temperature begins to drop significantly. In Lake Erie, survival time varies depending on water temperature, clothing, body composition, and physical condition. In water near 40 degrees Fahrenheit, exhaustion or unconsciousness can occur within an hour, sometimes sooner. In slightly warmer water, time extends but remains limited. Life jackets play a crucial role during the initial cold shock phase. Because breathing control is compromised, a person may struggle to keep their head above water. A properly fitted life jacket maintains buoyancy, even if the individual cannot coordinate movements effectively. Many cold water drownings occur because victims were not wearing life jackets at the moment of immersion. There is also a phenomenon known as cold incapacitation, Even if a person initially manages breathing, muscle cooling reduces strength rapidly. Swimming efficiency declines. A strong swimmer in warm water may not perform similarly in cold conditions. Overestimation of ability becomes dangerous. Lake Erie's recreational culture sometimes emphasizes summer activities. Beaches fill with swimmers during warm months. Fishing tournaments draw participants throughout the year. Early and late season boating appeals to those seeking quieter conditions. During those shoulder seasons, cold water risk is highest. Another factor often overlooked is air temperature misperception. A warm, sunny day can create false confidence. If air temperature is 65 degrees Fahrenheit, it feels mild. But if water temperature is 45 degrees, immersion remains life-threatening. Humans judge comfort by air exposure, not water exposure. Rescue timing is critical. Cold water slows movement and reduces survival time. Search and rescue teams train for rapid deployment during cold months. Helicopter and boat crews understand that minutes matter. Ice season introduces additional hazards. When Lake Erie freezes, particularly in the western basin, people sometimes venture onto the ice for fishing or recreation. Ice thickness varies widely. Warmer currents, wind-driven movement, and uneven freezing create weak spots. Falling through ice combines cold water shock with entrapment risk. Even when ice appears stable near shore, conditions farther out may differ. Snow cover can insulate ice, slowing thickening and hiding cracks. Rescue in icy water becomes more complex due to floating ice pieces and unstable surfaces. Commercial shipping operates mostly outside peak ice conditions, but transitional periods still present cold immersion risk. Crew members working on deck in cold months face increased danger if swept overboard by waves. Physiologically, cold water immersion also stresses the cardiovascular system. Rapid constriction of blood vessels increases blood pressure. For individuals with underlying heart conditions, the sudden shock can trigger arrhythmias or cardiac arrest. This risk extends beyond swimming ability. Educational campaigns increasingly emphasize 1-10-1 survival principles. 1 minute to control breathing. 10 minutes of meaningful movement before muscle cooling impairs coordination, and approximately 1 hour before unconsciousness due to hypothermia in cold water. While these numbers vary, they provide a practical framework. Clothing affects outcomes. Heavy clothing may initially provide insulation, but once saturated, it adds weight and restricts movement. However, modern cold water gear such as dry suits significantly increases survival time. Recreational boaters rarely wear such equipment outside specialized activities. Another subtle seasonal risk relates to temperature layering. In late spring and early summer, surface water may feel warm while deeper water remains cold. Wind-driven mixing or a fall from a boat into deeper water may expose individuals to colder temperatures than expected. Lake Erie's shallow depth reduces extreme thermal layering compared to deeper lakes, but localized cold pockets can still exist, especially near river inflows. Alcohol consumption contributes to seasonal accidents as well. Warmer days encourage social boating. Alcohol impairs judgment, coordination, and thermoregulation. In cold water, impaired reaction increases risk dramatically. Rescue equipment availability varies across shoreline communities. Popular beaches maintain lifeguard services during peak season. Remote areas may not. Boaters venturing offshore rely primarily on self-preparedness and communication devices. Weather forecasts often include water temperature reports, but not all users pay attention. Emphasis on wind and precipitation may overshadow immersion risk. Drowning statistics on Lake Erie reflect these patterns. A disproportionate number of fatalities occur outside peak summer warmth. Victims are frequently not wearing life jackets. Many incidents involve small boats or shoreline falls during cooler months. Public awareness efforts increasingly highlight the phrase "cold water kills" to emphasize that even inland lakes pose severe risk outside summer. This messaging counters assumptions that large bodies of fresh water are inherently less dangerous than oceans. Cold water shock connects directly to earlier themes. Sudden storms increase the chance of falling overboard. Steep waves destabilize vessels. Fog reduces visibility and complicates rescue. The lake's physical characteristics shape not only wave behaviour but also seasonal temperature dynamics. As with other hazards discussed, cold water risk is not constant. During late July afternoons, Lake Erie can feel inviting and warm, but safety depends on context. The same lake that supports swimming and recreation in summer becomes physiologically hostile in early spring. Understanding seasonal variation requires recognising that danger on Lake Erie shifts forms rather than disappearing. When waves are manageable, temperature may be the primary risk. When temperature is comfortable, storms or currents may take precedence. Currents themselves introduce additional complexity beneath the surface, moving water in ways that are not always visible, yet significantly influence both swimmers and vessels. From the shoreline, Lake Erie often appears still. Even on days when small waves roll toward the beach, the broader body of water can look stable, almost flat beyond the nearshore chop. But beneath that surface, the water is rarely motionless. It moves in patterns that are not always obvious to the eye. Some of these movements are steady and predictable. Others are temporary, triggered by wind or pressure changes. Together, they form a hidden layer of motion that influences everything from swimming safety to large vessel navigation. When people hear the word current, they often think of strong ocean flows like the Gulf Stream. Large-scale currents in Lake Erie are not as powerful as those in major oceans, but they are significant enough to shape conditions in ways that matter. The lake's primary long-term circulation generally follows a west-to-east pattern. Water enters mainly through the Detroit River at the western end and exits via the Niagara River in the east. This inflow and outflow create a baseline directional movement. However, wind often overrides this baseline flow. Because Lake Erie is shallow and elongated, sustained winds can push surface water across large distances quickly. When strong west winds blow for hours or days, they drive surface water toward the eastern end of the lake. Water levels there rise. Meanwhile, water levels in the western basin fall. This imbalance does not remain permanent. Once winds decrease or shift direction, gravity pulls the displaced water back toward equilibrium. That oscillation is known as a Seiche. A Seiche is essentially a standing wave that forms within an enclosed or partially enclosed body of water. It is not a surface wave like those created directly by wind friction. Instead, it is a large-scale sloshing motion of the entire water body. Think of water in a bathtub when pushed from one end to the other. It does not immediately settle, it rocks back and forth. On Lake Erie, Seiches can cause water level differences of several feet between opposite ends. In extreme historical cases, differences have exceeded 10 feet. Shoreline communities at one end may experience temporary flooding, while the opposite end sees unusually low water levels. Harbours can drain partially. Boats may be left grounded unexpectedly. For swimmers and small craft operators, these water level changes can alter nearshore conditions rapidly. Areas that were waist deep may become chest deep or vice versa. Structures such as docks and piers may experience unexpected stress from fluctuating water pressure. Seiches are triggered primarily by sustained winds, but atmospheric pressure changes can also contribute. A passing low-pressure system reduces atmospheric weight pressing down on the water surface. This slight reduction allows water to rise slightly beneath the low-pressure area. When combined with wind-driven displacement, the effect can amplify oscillation. Seiches do not end immediately when winds stop. The lake continues rocking back and forth for hours, sometimes days, gradually losing energy through friction and shoreline interaction. This means that even after skies clear and winds calm, water levels may still fluctuate. Beyond Seiches, there are longshore currents that move parallel to the shoreline. These currents form when waves approach the shore at an angle. As waves break, they push water along the beach. Longshore currents can carry swimmers sideways, sometimes without them noticing at first. A swimmer entering the water at one point may find themselves far down the beach minutes later. Rip currents, while more commonly associated with ocean beaches, also occur on Lake Erie. These form when water pushed towards shore by waves needs to return to the open lake. If there is a channel or break in sandbars, water funnels outward in a narrow, faster-moving stream. Swimmers caught in rip currents may feel pulled away from shore. Panic often follows, increasing exhaustion risk. Unlike visible surface waves, currents may not present obvious surface cues. Slight colour differences or surface texture changes sometimes reveal their presence, but casual beachgoers may not recognise these signs. The lake's basin structure also influences internal water movement. In summer, portions of Lake Erie, especially the deeper eastern basin, can experience partial thermal stratification. Warmer water sits above cooler water. Wind-driven mixing disrupts these layers, redistributing oxygen and temperature. When strong winds suddenly mix layers, water density differences shift rapidly, affecting current patterns. River inflows add localized current zones. The Detroit River brings substantial water volume into the western basin. Near that inflow, directional currents can be stronger than in open water. Similarly, water exiting through the Niagara River accelerates toward the eastern outlet. Boats operating near river mouths must account for these flows. Storm surges combine wave energy and water displacement. While Lake Erie does not experience tidal surges like coastal oceans, wind-driven water piling up along shorelines can resemble storm surge behaviour. During intense wind events, especially from the west, eastern shoreline communities may see rapid water rise. Infrastructure near waterlines can be affected. Another less visible movement involves undertow, the downward pull of water beneath breaking waves. When waves break strongly in shallow areas, water moves shoreward at the surface and then returns seaward below. While not typically as powerful as ocean undertows, this motion can destabilize swimmers in turbulent conditions. Subsurface currents also influence navigation for larger vessels. While their effect on heavy ships is less dramatic than surface waves, persistent directional flows affect steering and fuel efficiency. Captains factor these movements into route planning. For small craft, hidden water movement can feel unpredictable. A kayak drifting sideways despite calm air may be experiencing a longshore current. An anchored boat swinging unexpectedly might be reacting to subtle shifts in surface flow. Seiches can also create sudden current reversals in connecting rivers and harbours. When water level rises at one end of the lake, outflow through the Niagara River increases. When water sloshes back, outflow reduces or even temporarily reverses in certain tributaries. These reversals complicate docking and river navigation. Meteorologists monitor wind patterns closely because sustained directional winds predict Seiche potential. Emergency management agencies issue advisories when significant water level shifts are expected. Shoreline residents may be warned about possible flooding or low water hazards. In winter, ice cover modifies current behaviour. Ice dampens surface wave action, but does not eliminate subsurface movement entirely. Wind can push large ice sheets, driven partly by underlying water motion. Pressure ridges form where ice compresses. Open leads may appear where currents maintain thinner ice. Ecologically, currents influence nutrient distribution. Agricultural runoff entering the western basin can be transported eastward. Algal blooms may follow current patterns. Oxygen levels fluctuate based on mixing intensity. From a rescue perspective, understanding current direction is critical. When a swimmer or boater goes missing, search patterns account for likely drift based on wind and current data. Misjudging hidden movement can delay recovery. The term hidden applies because these motions are often invisible from casual observation. A calm-looking surface does not imply still water. The absence of visible waves does not mean the absence of flow. Lake Erie's shallow depth again amplifies responsiveness. Wind energy transfers quickly to the entire water column. With less vertical volume, the lake's mass shifts more readily than deeper systems. Seiche oscillations therefore become more pronounced relative to overall depth. Human familiarity sometimes reduces caution around these phenomena. Because Lake Erie lacks ocean tides, many assume water levels remain stable, yet wind-driven oscillations can produce changes rivaling small tidal ranges elsewhere. Boaters anchored in shallow areas sometimes find themselves unexpectedly aground when water levels drop due to Seiches effects. Conversely, docks built for average water levels may be submerged temporarily when levels rise. Each of these movements adds complexity to the lake's behaviour. Waves shape the surface, storms reshape the atmosphere above, cold water shapes physiological response. Currents and Seiches reshape the entire body of water beneath. Understanding Lake Erie requires looking beyond what is immediately visible. Beneath apparent calm lies constant motion. And beyond physical forces alone, there is another element that consistently influences how these forces translate into accidents and statistics, human decision-making and perception. When discussions about Lake Erie's dangers focus only on weather, waves, or water temperature, an important piece of the picture can get overlooked. The lake itself behaves according to physical laws. Wind moves water, temperature differences drive storms, currents shift predictably when pressure or wind changes. But accidents rarely result from environmental factors alone. Human perception, judgment, routine, and sometimes simple habit often shape how those environmental factors translate into real incidents. Lake Erie, perhaps more than some other large bodies of water, sits close to dense population centres. Cities line its shores. Highways lead directly to marinas, beaches, and boat launches. For millions of people, visiting the lake does not require elaborate planning. It can be a weekend outing, a short fishing trip after work, or an afternoon swim. Accessibility encourages familiarity. Familiarity encourages comfort, and comfort, while useful, sometimes reduces caution. People who grow up near the lake often see it regularly. Calm summer days reinforce the impression that conditions are manageable most of the time. Family stories emphasize recreation rather than hazard. The lake becomes part of daily scenery. Over time, this normalcy shapes perception. Risk feels abstract because routine exposure rarely results in visible consequences. Overconfidence often develops gradually rather than suddenly. A boater who has gone out dozens of times without incident may begin to assume future trips will be similarly uneventful. Weather forecasts that proved accurate in the past build trust, sometimes more trust than uncertainty warrants. Equipment that performed well repeatedly may be assumed reliable indefinitely. Psychologists studying risk perception describe a phenomenon sometimes called normalization of risk. When individuals repeatedly experience a potentially hazardous environment without negative outcomes, they adjust their internal sense of danger downward. The environment feels safer not because it has changed, but because previous experiences lacked adverse events. Lake Erie's variability complicates this process. Many days genuinely are calm and safe. That reinforces the perception that caution can occasionally relax. Yet the same physical conditions discussed earlier mean that change can occur faster than expected. The gap between perceived stability and actual variability becomes a factor. Recreational boating statistics often reflect this dynamic. Incidents frequently involve individuals with some experience, not exclusively novices. Familiar operators sometimes skip safety checks. Life jackets remain stowed instead of worn. Fuel levels may be estimated rather than confirmed. Weather updates may be glanced at once rather than monitored continuously. Familiar shorelines also influence swimmers. Beaches visited repeatedly feel predictable. Currents, however, change with wind direction and wave angle. A beach safe last week may present stronger longshore flow today. Visitors who rely on memory rather than current observation sometimes misjudge conditions. Another human factor involves group behaviour. When multiple people head out together, responsibility can diffuse. Each person assumes someone else checked the forecast, verified equipment, or confirmed safety protocols. Social psychologists refer to this as diffusion of responsibility. It occurs in many contexts, From workplace settings to outdoor recreation, alcohol consumption intersects with recreational lake use as well. Boating culture often includes social elements. Alcohol impairs judgment, coordination, and reaction time. It also affects thermoregulation, which becomes relevant if someone enters cold water unexpectedly. Accident reports frequently cite alcohol as a contributing factor, though rarely the sole cause. Technology introduces its own dimension to familiarity. GPS navigation, smartphone weather apps, and marine electronics improve safety when used correctly. However, reliance on technology sometimes replaces fundamental situational awareness. Devices can fail, batteries deplete, signal coverage fluctuates. Operators accustomed to constant electronic guidance may feel disoriented when systems are unavailable. There is also a psychological comfort associated with larger vessels. Owners of bigger boats sometimes perceive themselves as insulated from hazards affecting smaller craft. While larger vessels do offer stability advantages, they are not immune to steep waves, mechanical failure, or navigation errors. Confidence based solely on vessel size can lead to underestimating environmental forces. Professional mariners address familiarity differently. Commercial shipping crews receive structured training emphasizing standard operating procedures. Checklists reduce reliance on memory alone. Routine drills maintain readiness. Recreational users often operate without comparable institutional support, relying instead on personal habits. Fishing culture provides another example. Anglers often develop detailed local knowledge about fish behavior, seasonal patterns, and productive locations. This knowledge sometimes fosters confidence extending beyond fishing itself into navigation and weather assessment. Expertise in one domain can spill into perceived expertise in others, even when conditions differ. Rescue professionals frequently note that distress calls sometimes come from individuals who initially believed conditions were manageable. A weather change that might prompt early return in a cautious operator may instead lead an overconfident operator to continue longer, reducing margin for safe retreat. Time pressure contributes as well. A planned outing may involve schedules, reservations, or social commitments. When conditions begin deteriorating, people sometimes continue rather than cancel plans. The psychological investment in an activity can override emerging caution signals. Economic factors play a role for commercial operators. Fishing crews, charter captains, and delivery services sometimes operate under financial pressure. Cancelling trips affects income. While safety remains priority in professional settings, economic realities influence decision-making frameworks. Cultural narratives about lakes also influence perception. Inland lakes are often framed as safer than oceans. Absence of tides and saltwater hazards reinforces this view. While certain ocean risks are indeed absent, Lake Erie's specific characteristics introduce different hazards that familiarity can obscure. Experience level does not eliminate risk but changes its nature. Novices may lack technical skills. Experienced individuals may underestimate variability. Both groups benefit from ongoing awareness rather than static confidence. Another psychological element involves optimism bias. People generally believe negative events are less likely to happen to them than to others. This bias influences many activities, from driving to outdoor recreation. On Lake Erie, optimism bias may lead individuals to assume storms will bypass them, equipment will function reliably, or rescue will be readily available. Emergency preparedness often reflects this bias. Safety equipment may exist on board but not be readily accessible. Distress flares stored but expired. Radios present but not tested. Life jackets available but not worn. The gap between theoretical preparedness and practical readiness can widen over time. Educational campaigns attempt to address these factors by emphasizing routine safety habits. Wear life jackets consistently. Check forecasts repeatedly. File float plans before departure. Maintain equipment proactively. These recommendations aim to counteract familiarity-induced complacency. Community knowledge sharing also helps. Local boating clubs, fishing groups, and marina networks often exchange observations about changing conditions. Informal communication supplements formal forecasting. Training programs increasingly include psychological awareness components. Understanding how overconfidence develops helps individuals recognize it in themselves. Structured reflection after outings encourages continuous learning rather than assumption of mastery. It's also worth noting that familiarity can be beneficial when balanced with awareness. Long-term lake users often detect subtle cues novices miss. Wind shifts, cloud formation patterns, and watercolor changes provide early signals. The key difference lies in whether familiarity breeds attentiveness or complacency. Human factors do not act independently of physical conditions. Overconfidence becomes hazardous when combined with sudden storms, steep waves, cold water, or reduced visibility. Familiarity shapes response time. Caution increases margins for adaptation. Lake Erie's accessibility ensures that human interaction with it will remain high. Beaches, marinas, shipping routes, and waterfront communities all depend on the lake. Managing risk therefore involves not only understanding environmental science, but also understanding human psychology. And while recreational use often dominates public perception, commercial shipping has its own long history of adapting to these same human and environmental interactions, shaping safety practices that evolved over decades of experience. Long before recreational boating became common on Lake Erie, commercial shipping defined the lake's relationship with people. Grain, coal, lumber, iron ore, machinery, and countless other goods moved across its waters. Cities along the shoreline grew because ships could move cargo efficiently between inland North America and Atlantic trade routes. Harbours expanded. Shipyards appeared. Navigation channels were dredged. The lake became part of an economic system that depended on consistent movement of vessels. That dependence did not remove the lake's unpredictability. It simply meant ships continued operating even when conditions were less than ideal. Over time, patterns of hazard became clear. Some were environmental, tied to waves, fog, storms, and currents already discussed. Others involved technology limitations, human decision-making, and evolving industrial demands. Early commercial shipping on Lake Erie relied heavily on sail. Schooners dominated the 19th century. These wooden vessels carried cargo in relatively shallow draught suitable for the lake's depth. Sail propulsion offered efficiency but limited control when winds shifted suddenly. A strong following wind might push a vessel faster than intended. A headwind might stall progress entirely. If a storm developed, manoeuvring options narrowed. Captains learned to read sky conditions carefully. Cloud formations, barometric pressure, wind direction shifts, and water surface texture all provided clues, yet even experienced sailors could misjudge timing. A storm forming faster than expected could trap a ship far from safe harbour. Harbours themselves presented hazards. Many Lake Erie ports were located at river mouths or behind sandbars. Entering harbour during rising waves required precision. Waves steepened as they approached shallow entrances. Breakwaters, designed to reduce wave energy inside harbours, sometimes reflected waves unpredictably near entrances. Ships attempting refuge occasionally grounded or collided with structures. The introduction of steam power in the mid-19th century changed navigation dynamics. Steamships could maintain headway independent of wind direction. They could attempt to outrun storms or hold position more effectively. However, steam engines introduced mechanical complexity. Boiler maintenance, fuel management, and engine reliability became critical. Mechanical failure during rough weather posed significant danger. Without propulsion, a vessel lost the ability to orient favourably to waves. Waves striking broadside increased rolling. Water ingress became more likely. Crew workload increased dramatically. Steamships also tended to be larger than earlier sailing vessels. Increased cargo capacity improved economic efficiency, but increased consequences when accidents occurred. A large cargo ship lost in a storm represented both human tragedy and substantial economic loss. Lake Erie's shallow depth influenced hull design. Ships required drafts suitable for variable water levels. Seasonal fluctuations, Seiches, and sediment movement affected channel depth. Dredging programs attempted to maintain navigable routes, but shoaling remained an ongoing concern. Navigation aids evolved gradually. Early lighthouses provided fixed visual reference points. Lightships marked hazardous shoals. Buoys indicated channels. Fog signals accompanied some lighthouses to aid navigation during low visibility. These aids reduced risk but did not eliminate it. Fog remained a persistent hazard for commercial shipping. Large vessels moving slowly still required adequate stopping distance. Reduced visibility increased collision risk with other ships, fishing vessels, and stationary structures. Sound signalling protocols developed to mitigate this risk, but interpretation challenges persisted. The late 19th and early 20th centuries saw increased industrialization around Lake Erie. Steel production, coal transport, and grain export intensified shipping traffic. Congestion in busy shipping corridors increased collision potential. Coordination between vessels relied on visual signals, whistles, and later radio communication. Radio technology marked a significant safety improvement. Wireless telegraphy allowed ships to communicate distress signals and coordinate navigation. Weather updates could be transmitted. Rescue operations improved as distress calls reached shore more quickly. Despite technological advances, severe storms continued affecting commercial fleets. Autumn gales were particularly notable. Warm lake water interacting with cold incoming air masses created intense low-pressure systems. Sustained winds built steep waves across the lake's long fetch. Historical storm reports describe cargo ships struggling to maintain course, deck cargo shifting, and structural stress on hulls. Cargo type influenced risk as well. Grain cargoes, if improperly secured, could shift during heavy rolling. Coal cargo created dust that sometimes interfered with equipment. Liquid cargo introduced sloshing dynamics, affecting vessel stability. Crew working conditions during storms were demanding. Deck operations required coordination under high winds and wave spray. Visibility reduction from spray and precipitation complicated tasks. Safety equipment standards improved gradually, but earlier periods saw limited protective gear. Winter shipping historically paused due to ice. As ice-breaking technology improved, some navigation extended into colder months. Ice introduced new hazards. Hull abrasion, blocked channels, reduced maneuverability, and limited rescue access. Lake Erie's relatively quick freezing compared to deeper lakes made winter operations particularly complex. Engineering improvements gradually enhanced vessel safety. Steel hull construction replaced wood, increasing durability. Watertight compartments reduced flooding risk. Improved bilge pumps managed water ingress more effectively. Navigation instruments became more precise. Electronic navigation systems in the late 20th century transformed commercial shipping further. Radar allowed detection of other vessels and landforms in fog or darkness. Satellite navigation provided accurate positioning. Weather forecasting models improved with satellite data. Despite these advances, commercial shipping still respects Lake Erie's environmental conditions. Modern freighters adjust schedules based on forecasted storms. Harbour authorities issue advisories. Pilots familiar with local conditions guide vessels into complex ports. Human factors continue influencing safety. Fatigue among crew members can impair decision-making. Long shifts, particularly during peak shipping seasons, require careful management. Training programs emphasize situational awareness, emergency procedures, and equipment familiarity. Economic pressures also remain relevant. Shipping schedules connect multiple lakes and ports. Delays affect supply chains. Decisions about departure timing balance safety with the logistical demands. Industry standards encourage conservative judgment, but commercial realities shape operational choices. Environmental regulations have added another dimension. Pollution prevention, ballast water management, and emission standards influence ship operations. Compliance procedures sometimes add operational complexity, but contribute to long-term environmental sustainability. Lake Erie's ecological sensitivity, due partly to its shallowness, means environmental incidents can have noticeable impact. Spills or discharges disperse differently than in deeper lakes. Shipping companies invest in prevention measures accordingly. Port infrastructure evolved alongside shipping technology. Breakwaters strengthened. Channel dredging improved consistency. Dock equipment modernized. Yet infrastructure must adapt continuously to sediment movement and changing water levels influenced by climate variability. Climate patterns themselves influence shipping hazards. Warmer winters may reduce ice cover, extending shipping seasons but increasing storm exposure. Changes in precipitation patterns affect river inflow and sediment transport. Long-term monitoring informs infrastructure planning. Commercial shipping culture emphasizes procedural discipline. Checklists, standardized communication protocols, and continuous training aim to reduce human error. Lessons learned from historical incidents inform current practices. Lake Erie's role as a connector between Upper Great Lakes and the Atlantic via the Welland Canal ensures ongoing traffic. Cargo volume remains substantial. Economic reliance on lake shipping persists. Historical shipwreck records, when examined alongside modern incident data, show improvement in safety outcomes. Fatalities and major losses have decreased relative to traffic volume. Technology, training and regulation all contributed. Yet the underlying environmental context remains unchanged. Shallow depth still accelerates wave formation. Fog still develops under familiar temperature contrasts. Storm tracks still cross the region regularly. Currents and Seiches still shift water levels. Commercial shipping therefore represents an ongoing adaptation process rather than a solved problem. Operators continuously integrate new technology, updated forecasts, and historical experience into daily decision-making. And while commercial vessels operate under structured professional frameworks, recreational boating on Lake Erie presents a different pattern of hazards shaped by access, personal judgment, and varying levels of training. By the time commercial shipping had established long-standing routes across Lake Erie, another pattern was beginning to take shape. Smaller boats, privately owned or rented, started appearing in greater numbers. Improvements in engine reliability, declining costs of fiberglass hull construction, and expanded marina infrastructure made boating accessible to far more people than in earlier centuries. Fishing, sailing, water skiing, cruising, and casual sightseeing all became part of everyday lake culture. This growth in recreational boating changed the overall risk landscape. Commercial ships, while large and numerous, operate under strict training standards and regulatory frameworks. Recreational boating, by contrast, involves individuals with a wide range of experience levels, safety awareness, and equipment preparedness. The result is a different accident pattern, one shaped less by large-scale catastrophic losses and more by numerous smaller incidents. Accident reports from recent decades show recurring themes. Weather misjudgment ranks among the most common. Boaters depart under acceptable conditions, expecting stability, only to encounter strengthening winds or storms faster than anticipated. Because Lake Erie's shallow depth allows waves to build quickly, small vessels may become overwhelmed before operators can return to shore. Mechanical failure also appears frequently. Unlike commercial vessels with scheduled maintenance protocols, recreational boats vary in upkeep. Engines that have sat unused over winter months may develop issues when reactivated. Fuel contamination, battery degradation, and cooling system problems sometimes surface mid-trip. In calm conditions, these may be inconveniences. In rising waves or poor visibility, they become safety concerns. Life jacket usage continues to be a critical factor. Safety campaigns emphasize wearing life jackets at all times on open water, yet many recreational users keep them stored rather than worn. Accident data consistently show that a high percentage of drowning victims were not wearing flotation devices when incidents occurred. The combination of unexpected immersion, cold water shock outside peak summer, and lack of flotation reduces survival chances significantly. Navigation errors represent another category. GPS and chart plotters have improved accuracy, but over-reliance on electronics sometimes replaces basic situational awareness. Battery failure, signal interruption, or unfamiliarity with device operation can leave operators uncertain about location. Fog, already discussed, compounds these issues by removing visual references. Collision incidents occur most often in congested areas near marinas, popular fishing spots, or busy shoreline recreation zones. Speed misjudgment, distraction, or impaired visibility contributes. Unlike commercial ships with dedicated watchkeeping crews, recreational boats often have a single operator managing navigation, passengers, and equipment simultaneously. Alcohol remains a documented factor in a notable portion of recreational boating accidents. Impaired judgment affects reaction time, balance, and decision-making. Combined with environmental stressors like sun exposure, wind, and motion, alcohol's effect can intensify. Seasonal patterns are evident. Summer sees the highest volume of recreational activity, and therefore the highest number of incidents numerically. However, fatality rates per outing tend to increase in shoulder seasons when water temperatures remain low, but activity continues. Early spring fishing and late autumn boating carry elevated cold water immersion risk. Equipment variation contributes to accident diversity. Small fishing boats, personal watercraft, sailboats, pontoons, and kayaks each present distinct operational characteristics. Kayaks and paddleboards are particularly vulnerable to sudden wind shifts due to limited propulsion speed. Personal watercraft operate at higher speeds, increasing collision risk if situational awareness lapses. Fishing-specific incidents include entanglement in lines, overloading small boats with gear or catch, and distraction while focusing on fishing tasks. Charter fishing operations, though professionally run, still navigate crowded waters where recreational vessels operate unpredictably. Technological improvements have altered rescue patterns. Emergency position indicating radio beacons, marine radios, and smartphone distress apps allow faster communication. Coast Guard and local rescue services respond more quickly than in earlier eras. Helicopter deployment, thermal imaging, and coordinated search grids improve survival outcomes. Despite these improvements, prevention remains more effective than rescue. Public education campaigns stress pre-departure checks, verifying fuel levels, testing communication devices, reviewing weather forecasts, and informing someone ashore of plans. These practices reduce response time if problems arise. Marina infrastructure expansion has made access easier, but sometimes encourages higher traffic density. Launch ramps in urban areas see heavy weekend use. Congestion near launches increases collision potential. Novice operators may feel pressured by waiting crowds, leading to hurried preparations. Rental boating introduces another dynamic. Visitors unfamiliar with Lake Erie's specific conditions may rely on general boating experience from other lakes or coastal areas. Rental orientation sessions vary in depth. Time constraints sometimes limit thorough safety briefings. Sailing communities bring a different set of considerations. Sailboats respond differently to wind than motorboats. Skilled sailors anticipate wind shifts, but sudden storm gusts can still overpower smaller craft. Reefing sails quickly becomes essential. Equipment failure in rigging can escalate rapidly under load. Night boating has increased with improved lighting technology. LED navigation lights, illuminated instrumentation, and shoreline lighting make nighttime outings more feasible. However, darkness reduces visual depth perception. Fog at night further complicates navigation. Fatigue after long daytime activity may impair nighttime decision-making. Personal flotation device design has improved comfort, encouraging adoption. Inflatable life jackets, for example, provide mobility while offering buoyancy when activated. Adoption rates continue rising, though universal usage remains a goal. education programs offered by Coast Guard auxiliaries, boating clubs and community colleges emphasise situational awareness. Topics include wave interpretation, weather monitoring, emergency procedures, and equipment maintenance. Participation varies, but trained boaters statistically show lower accident rates. Environmental monitoring contributes indirectly to safety. Real-time buoy data provides wave height, wind speed, and water temperature information accessible online. Savvy boaters check these data sources before departure and during trips when connectivity allows. Social media has created informal safety networks. Boaters share observations about sudden weather changes, floating debris, or navigation hazards. While not a substitute for official forecasts, these peer reports supplement awareness. Infrastructure such as breakwaters, channel markers, and harbour improvements continue evolving. Maintenance ensures reliability of aids to navigation. Budget constraints sometimes affect maintenance schedules, highlighting the importance of ongoing investment. Search and rescue case studies often highlight quick decision-making as a positive factor. Operators who recognise deteriorating conditions early and seek shelter promptly tend to avoid escalation. Delayed decisions frequently appear in more serious incidents. Environmental stewardship intersects with safety as well. Debris from storms, abandoned fishing gear, and shoreline runoff create additional hazards. Cleanup initiatives reduce these risks while improving ecological health. Lake Erie's recreational boating culture remains vibrant. Fishing tournaments, sailing regattas, family outings, and wildlife observation all contribute to regional identity. Safety awareness aims not to discourage participation, but to ensure it continues sustainably. Modern accident patterns show fewer large-scale disasters than in historical commercial shipping eras. Yet cumulative smaller incidents maintain the lake's statistical reputation. Understanding patterns allows targeted prevention strategies, and beyond recreational activity alone, forecasting technology itself has evolved significantly, influencing how both commercial and recreational operators anticipate changing conditions and adjust their decisions accordingly. Weather awareness on Lake Erie has never been optional, but the way people gather and interpret that information has changed dramatically over time. Early sailors relied almost entirely on direct observation. The sky, wind direction, cloud height, barometric pressure, and even animal behaviour all provided clues. These methods were not guesswork in the casual sense. Experienced mariners developed strong observational skills, and many could anticipate weather shifts with surprising accuracy. Still, those observations had limits. A storm forming beyond the visible horizon gave little warning until its effects were already arriving. In the 19th century, systematic weather forecasting barely existed. Meteorology as a formal science was still developing. Communication technology also constrained information flow. Telegraph networks eventually allowed weather reports from distant locations to be transmitted, but this infrastructure took time to expand around the Great Lakes region. Before that, a captain departing from Cleveland or Buffalo might have no reliable information about conditions developing farther west. Barometers were among the earliest widely used forecasting instruments on board ships. Falling atmospheric pressure often precedes storms. Captains learned to monitor pressure trends carefully. A rapid drop signalled caution. However, a barometer alone could not reveal storm trajectory, speed, or intensity. It provided warning but not detailed guidance. Cloud observation played a central role. Certain cloud formations, particularly towering cumulonimbus or rapidly thickening altostratus layers, indicated atmospheric instability. Mariners memorized these visual signs. Yet Lake Erie's relatively low horizon sometimes limited early detection, especially when fog or haze obscured distant cloud buildup. Lighthouses provided another layer of safety, but mainly for navigation rather than forecasting. Lightkeepers sometimes relayed informal weather observations, and some stations eventually included basic meteorological instruments. These data contributed gradually to regional understanding of lake weather patterns. The late 19th century saw the beginnings of organised weather services. Government meteorological agencies started collecting data from multiple locations simultaneously. Telegraph lines allowed sharing of pressure readings, temperature data, and wind observations. This network enabled early storm tracking. Forecasters could identify low-pressure systems moving across the continent and issue general advisories. These early forecasts were broad. They described expected conditions over large regions rather than specific lake segments. Timing precision remained limited. Still, the ability to warn ships before departure marked a significant improvement. By the early 20th century, radio communication began transforming maritime safety. Ships could receive weather bulletins while underway. This reduced reliance solely on departure forecasts. However, radio coverage varied, and reception quality depended on atmospheric conditions and equipment capability. Weather buoys began appearing later, providing direct measurements from the lake itself. These buoys recorded wind speed, wave height, temperature, and pressure. Data transmitted ashore improved forecast accuracy. Mariners gained access to real-time information rather than relying exclusively on coastal stations. Aircraft reconnaissance during certain periods added observational capability. Pilots could observe storm systems over water, where ground stations were absent. Though not continuous, such observations contributed to understanding storm development patterns over the Great Lakes. Satellite technology marked one of the most significant advances in weather forecasting. Beginning in the mid-20th century, satellites provided continuous observation of cloud systems, temperature gradients, and storm movement. For Lake Erie, satellite imagery revealed how weather systems interacted with the lake surface, including moisture pickup and cloud formation patterns. Satellite data improved storm track prediction substantially. Forecasters could see systems approaching from hundreds of miles away. Warning-led times increased. Mariners gained more opportunity to adjust plans. Doppler radar introduced another major improvement. Radar detects precipitation intensity, storm rotation, and wind velocity. Great Lakes coastal radar stations monitor approaching storms continuously. This capability allows issuance of severe thunderstorm warnings, gale warnings, and small craft advisories with much greater precision than earlier methods. Modern forecasting models combine satellite data, radar observations, buoy measurements, aircraft reports, and land-based stations. Sophisticated computer models simulate atmospheric physics. These models incorporate temperature gradients, moisture levels, pressure systems, and wind dynamics. Output provides probabilistic forecasts, including wind speed ranges, wave height predictions, and precipitation likelihood. Forecast accuracy has improved significantly over decades. Short-term forecasts, especially within 24 to 48 hours, are generally reliable. Longer-term outlooks carry more uncertainty, but still guide planning. Marine-specific forecasts now include parameters tailored to boating needs. Wind direction, sustained wind speed, gust potential, wave height, wave period, water temperature, and visibility expectations are standard components. Hazard alerts such as small craft advisories or gale warnings highlight elevated risk. Communication channels have expanded dramatically. Weather radios broadcast continuous updates. Smartphone apps provide alerts, radar imagery, buoy data, and forecast updates instantly. Internet connectivity allows access to detailed marine forecasts before departure, and often during trips near shore. Chart plotters integrated with weather data stream display forecast overlays directly on navigation screens. Some systems update automatically via satellite or cellular connections. Operators can see predicted wind shifts relative to planned routes. Despite technological progress, forecasting remains probabilistic. Atmosphere and water interactions involve complex physics. Small initial variations can produce different outcomes. Forecasts describe likely scenarios rather than certainties. Understanding this limitation remains important. Human interpretation of forecasts introduces another layer. Technical terminology such as chance of thunderstorms or isolated squalls may be understood differently by individuals. Some interpret probability conservatively, others treat it optimistically. Education helps bridge this gap. Lake Erie's rapid response to atmospheric changes still challenges forecasters. Shallow water warms and cools quickly, affecting local stability. Localized storms sometimes develop faster than models predict. Forecasters issue updates frequently to address evolving conditions. Historical comparisons show dramatic improvement. In the 1800s, captains sometimes learned of storms only when winds increased. Today, alerts often precede storm arrival by hours. Response time has improved accordingly. Commercial shipping integrates forecasting into operational planning systematically. Routes adjust based on predicted wind fields. Departure times shift to avoid peak storm intensity. Professional meteorologists sometimes consult directly with shipping companies. Recreational boaters benefit from the same data, but may use it less systematically. Casual users might check forecasts only before departure. Continuous monitoring during outings improves safety but requires habit formation. Public education campaigns emphasize interpreting marine forecasts specifically rather than general city forecasts. Conditions on the lake often differ from inland conditions. Wind speeds over open water typically exceed those on land due to reduced friction. Wave forecasts deserve particular attention. Many accidents occur when wave height exceeds vessel capability. Forecasts include both significant wave height averages and potential maximum waves. Understanding the difference helps operators assess conditions realistically. Visibility forecasts incorporate fog probability. Temperature and humidity forecasts help anticipate fog formation. Early awareness allows route adjustments or trip postponement. Climate variability influences forecasting trends. Warmer average temperatures alter seasonal storm patterns. Ice cover duration has shown variability in recent decades. These changes require ongoing model adjustment. Environmental monitoring networks continue expanding. Additional buoys, improved satellite sensors, and enhanced computational models refine predictive capability. Data assimilation techniques integrate observations into models continuously, improving short-term accuracy. Emergency alert systems now reach broader audiences. Smartphone push notifications, marine radio broadcasts, and digital signage at marinas all disseminate warnings. Rapid communication reduces surprise. Still, forecasting does not eliminate risk entirely. Equipment failure, sudden localized storms, and human misinterpretation persist. Forecasting provides tools, not guarantees. The evolution from observation-based forecasting to model-driven prediction illustrates broader technological progress. Each advancement has reduced uncertainty incrementally. Yet Lake Erie's physical characteristics continue to demand respect. Forecasting accuracy also influences perception of safety. Increased confidence in forecasts may encourage activity. Balanced understanding recognizes both improved prediction and residual uncertainty. Education remains central. Training programs teach how to read marine forecasts, interpret radar imagery, and recognize early visual cues. Combining technology with observation produces the best outcomes. Local knowledge complements formal forecasting. Experienced lake users often notice subtle environmental cues. These observations sometimes align with forecast updates before official bulletins change. Forecasting also intersects with environmental monitoring. Algal blooms, water temperature trends, and ecological conditions relate partly to weather patterns. Integrated monitoring benefits both safety and environmental management. As forecasting technology continues improving, response strategies evolve. Rescue services coordinate using real-time weather data. Commercial shipping adjusts logistics dynamically. Recreational communities increasingly incorporate forecast awareness into planning culture. This ongoing adaptation reflects a broader pattern around Lake Erie. Environmental conditions shape human activity, and human understanding gradually improves through science and experience. And alongside weather forecasting, another environmental factor has shaped how people interact with the lake over time. Long-term environmental change and water quality challenges that influence both safety and ecosystem stability. When people describe Lake Erie as dangerous, they usually mean storms, waves, or cold water. But there is another kind of risk that has shaped the lake's reputation over time. It does not rise suddenly like a squall, and it does not announce itself with thunder. It develops gradually, often invisibly at first, through chemistry, biology, and human activity along the shoreline. Pollution and algal blooms have altered how the lake functions, and while they are not the same kind of immediate hazard as a storm, they create environmental stress that affects safety, recreation, and long-term stability. Lake Erie's shallow depth plays a central role here as well. Because the lake is relatively shallow, sunlight penetrates much of the water column in many areas, particularly in the western basin. Sunlight supports photosynthesis. Under natural nutrient levels, this contributes to a balanced aquatic ecosystem. But when nutrient concentrations increase significantly, especially phosphorus and nitrogen from agricultural runoff, sewage discharge, and urban stormwater, that same sunlight fuels rapid algal growth. In the mid-20th century, Lake Erie became widely known for severe pollution, industrial discharge, untreated sewage, and fertilizer runoff accumulated in the lake. Nutrient enrichment, known scientifically as eutrophication, caused explosive algae growth. By the 1960s and early 1970s, some observers described parts of Lake Erie as dead due to oxygen depletion in deeper waters and fish die-offs. The science behind this process is straightforward but powerful. Algae grow rapidly when nutrients and sunlight are abundant. When large algal blooms die, they sink and decompose. Decomposition consumes dissolved oxygen in the water. If oxygen levels drop too low, fish and other aquatic organisms cannot survive. In shallow basins, oxygen depletion can occur quickly during warm months when stratification limits mixing. Environmental regulation in the 1970s, including the Great Lakes Water Quality Agreement between the United States and Canada, reduced many direct industrial discharges. Wastewater treatment improved. Phosphorus levels declined for a time, and the lake's condition showed improvement. Fish populations recovered in several areas. However, nutrient runoff from agriculture remained a challenge. Modern farming practices, especially in the Western Basin watershed, contribute phosphorus to tributary rivers during heavy rainfall events. Because Lake Erie warms quickly in summer, these nutrients often fuel new algal blooms. Harmful algal blooms, particularly those caused by cyanobacteria such as microcystis, produce toxins. These toxins can contaminate drinking water supplies, harm pets and wildlife, and irritate skin upon contact. In 2014, a major bloom near Toledo, Ohio led to temporary shutdown of the municipal water supply for hundreds of thousands of residents. From a safety perspective, algal blooms create multiple challenges. First, water clarity decreases. Reduced visibility affects swimmers and divers. Murky water complicates search and rescue operations because submerged objects are harder to detect. Second, toxins present health risks. Swimmers exposed to contaminated water may experience skin rashes or gastrointestinal symptoms. Pets are particularly vulnerable if they drink affected water. Boaters navigating bloom-affected areas sometimes encounter thick surface scum. While not typically dangerous to vessels mechanically, such conditions can clog intake systems on smaller boats and interfere with cooling systems. Commercial vessels are less affected operationally, but must remain aware of environmental compliance issues. Algal blooms also alter ecosystem dynamics. Fish distribution changes when oxygen levels drop in certain basins. Hypoxic zones, areas of low oxygen, sometimes form in the central basin during summer stratification. Fish may migrate to more oxygenated areas, affecting fishing patterns and increasing boat traffic concentration in certain zones. Environmental stress influences long-term lake stability. Invasive species such as zebra and quagga mussels have further altered nutrient cycling. These mussels filter water, increasing clarity in some areas while redirecting nutrients toward nearshore zones. Clearer water allows deeper sunlight penetration, which can stimulate nearshore plant growth, including nuisance algae. Pollution also affects sediment quality. Contaminants from earlier industrial eras remain in some lakebed sediments. Storm-driven mixing or dredging activities can resuspend these sediments temporarily. While concentrations have declined compared to peak pollution periods, legacy contamination remains part of the environmental background. Climate patterns intersect with pollution issues. Warmer summers can intensify bloom growth. Increased frequency of heavy rainfall events transports more nutrients into tributaries. Shallow depth accelerates warming, creating favourable conditions for algae. Public awareness of environmental stress has grown significantly. Monitoring programs now track nutrient levels, toxin concentrations, and bloom size using satellite imagery and in-water sampling. Early warning systems notify municipal water authorities and the public when blooms intensify. For shoreline communities, visible blooms affect tourism and recreation. Beaches may close temporarily. Water sports participation declines. These economic impacts add another dimension to environmental stress beyond ecological effects. Despite these challenges, Lake Erie remains biologically productive. It supports one of the most valuable freshwater fisheries in North America. Walleye, perch, and other species thrive under managed conditions. The same nutrient input that causes problems when excessive also contributes to productivity when balanced. Management efforts aim to reduce nutrient loading through improved agricultural practices, wetland restoration, and stormwater management. Buffer strips along rivers reduce runoff. Upgraded wastewater facilities limit discharge. International cooperation remains essential because the lake spans national borders. Pollution hazards differ from storm hazards in timescale. Storms are acute events. Algal blooms develop over weeks. Oxygen depletion evolves gradually. Yet their influence on human activity can be significant. Water treatment adjustments, beach advisories, and fish consumption guidelines all respond to environmental monitoring. Recreational safety intersects with environmental health in subtle ways. Reduced water clarity may conceal submerged hazards. Shifting fish populations alter boating patterns. Public perception of water quality influences how people approach the lake. Environmental recovery since the mid-20th century demonstrates that management actions matter. The lake, once widely labelled as irreversibly damaged, has shown resilience. Fish populations rebounded, water quality improved in many metrics, yet continued vigilance remains necessary. Pollution and algal blooms illustrate how Lake Erie's shallow nature amplifies both positive and negative processes. Shallow water warms quickly, supporting productivity. It also supports rapid bloom growth when nutrients are excessive. Shallow basins respond quickly to both remediation and stress. Environmental stress adds complexity to the overall narrative of danger. While not directly causing most boating accidents, it shapes long-term interactions with the lake. Safe water is part of safe recreation. Understanding Lake Erie fully requires integrating physical hazards, human behaviour, and environmental management. Each dimension influences the others, and as environmental awareness has increased, so too have organised rescue efforts and coordinated safety systems designed to respond when conditions overwhelm preparation, reflecting decades of learning from both natural forces and human experience. When most conversations about Lake Erie focus on danger, they tend to revolve around storms, waves, shipping incidents, or water quality. Yet the lake is also a living ecosystem, constantly adjusting to environmental pressures, climate variability, and human activity. Wildlife patterns, fish populations, aquatic vegetation, and migratory species all reflect how the lake is changing. These ecological shifts do not always create immediate hazards in the dramatic sense, but they influence safety, recreation, and the long-term stability of the lake in ways that are often subtle at first. Lake Erie supports one of the most productive freshwater ecosystems in North America. Its relatively shallow depth allows sunlight to penetrate much of the water column, especially in the western basin. This sunlight fuels photosynthesis in algae, aquatic plants, and phytoplankton. When nutrient levels are balanced, this productivity supports rich food webs. Zooplankton feed on phytoplankton, small fish feed on zooplankton, larger predatory fish follow. Birds and mammals depend on those fish populations. This productivity has long made Lake Erie a major fishing destination. Commercial fisheries historically relied on species such as lake whitefish and yellow perch. Recreational fishing today focuses heavily on walleye, smallmouth bass, and perch. Fishing culture shapes boating patterns, marina development, and seasonal lake usage. However, productivity also makes the ecosystem sensitive to change. Nutrient fluctuations, invasive species introductions, and climate variability alter biological balance. These changes ripple outward. A shift in plankton populations affects fish distribution. Fish distribution affects boating patterns. Boating patterns influence safety exposure. Invasive species represent one of the most significant ecological shifts over the past several decades. Zebra mussels, first detected in the Great Lakes in the late 1980s, spread rapidly. Their close relative, the quagga mussel, followed. These mussels filter large volumes of water, removing plankton and increasing water clarity. Increased clarity allows deeper sunlight penetration, encouraging growth of aquatic vegetation and benthic algae near shorelines. Clearer water may sound beneficial, but ecological consequences are complex. Fish species adapted to murkier conditions adjust differently. Some thrive, others decline. Nutrient cycling shifts toward the lakebed. Nearshore algal blooms sometimes intensify due to redistributed nutrients. For swimmers and boaters, clearer water changes perception of depth and safety. Submerged hazards such as rocks, debris, or vegetation become more visible in some areas, yet dense plant growth can entangle propellers or swimmers unexpectedly. Aquatic vegetation mats sometimes accumulate along shorelines, affecting beach access. Another invasive species, the round goby, altered fish community dynamics. Gobies feed on mussels and compete with native fish for habitat. Predatory fish such as bass adapted by incorporating gobies into their diet. Fishing patterns shifted accordingly. Fish population cycles themselves influence recreational activity. Strong walleye years attract more anglers. Increased boat traffic concentrates in productive fishing zones. Congestion increases collision potential and navigational complexity. Bird populations reflect lake health as well. Migratory waterfowl use Lake Erie wetlands as stopover sites. Bald eagles, once rare due to pesticide impacts, have rebounded significantly. Their presence signals improved environmental conditions but also influences fish populations. Wetland ecosystems along the shoreline provide important buffers. They absorb storm runoff, filter pollutants, and provide habitat for fish spawning. Loss of wetlands due to development historically reduced these functions. Restoration projects aim to rebuild wetland areas, improving ecological resilience. Climate variability introduces additional complexity. Average water temperatures have shown upward trends over recent decades. Warmer water affects fish metabolism, reproduction timing, and species distribution. Some cold water species retreat to deeper basins or decline. Warm water species expand range. Longer ice-free seasons also alter ecological cycles. Historically, winter ice cover limited wave action, protected shorelines from erosion, and influenced spring nutrient mixing. Reduced ice cover exposes shorelines to winter storms and changes timing of ecological events. Earlier spring warming shifts spawning periods for certain fish species. Migratory bird arrival timing adjusts. These shifts cascade through food webs. Fisheries management adapts regulations accordingly to maintain sustainable populations. Aquatic plant growth responds strongly to temperature and nutrient levels. Increased plant density near shore can affect boating channels. Marina maintenance sometimes includes vegetation management to ensure navigability. Harmful algal blooms, discussed previously, interact with wildlife as well. Fish may avoid bloom areas due to low oxygen or toxin presence. Birds and mammals exposed to toxins may experience health effects. Monitoring programs track these impacts to guide public advisories. Pollution legacy effects persist in sediments. Certain contaminants accumulate in fish tissue. Fish consumption advisories inform anglers about safe intake levels. These advisories vary by species and location. Water clarity changes influence predator-prey relationships. Visual predators like walleye adjust hunting strategies when water becomes clearer. Behavioral adaptation occurs gradually, but affects catch rates and ecological balance. Shoreline erosion is another ecosystem-related factor. Storm-driven waves reshape coastlines. Loss of vegetation increases erosion vulnerability. Eroded sediments contribute to turbidity and nutrient transport. Climate-driven precipitation changes influence river inflow. Heavier rainfall events increase runoff carrying nutrients and sediments. Extended dry periods reduce inflow, affecting water levels and wetland health. Lake Erie's western basin, being shallowest, shows ecological changes most quickly. Temperature swings, nutrient inflow, and sediment resuspension all occur more readily there. The central and eastern basins respond more gradually, but still reflect long-term trends. Human recreation interacts with wildlife directly. Boating noise, shoreline development, and fishing pressure affect animal behaviour. Management agencies establish protected zones and seasonal restrictions to balance use with conservation. Wildlife presence can occasionally intersect with safety. Large fish schools attract concentrated fishing traffic. Bird flocks sometimes obscure visibility near shorelines. Aquatic vegetation mats may entangle propellers. Search and rescue operations consider wildlife patterns indirectly. Drift models incorporate wind, current, and sometimes biological indicators such as floating vegetation. Understanding local ecology improves prediction accuracy. Scientific research continues expanding knowledge of Lake Erie's ecosystem. Universities, government agencies, and international collaborations monitor water chemistry, species distribution, and climate interactions. Long-term datasets reveal trends not visible in short-term observation. Citizen science programs engage local communities. Volunteer monitoring of water clarity, bird populations, and shoreline conditions supplements professional research. Community involvement increases environmental awareness. Management strategies aim to maintain balance. Nutrient reduction initiatives, invasive species control, wetland restoration, and fisheries regulation all contribute. Success varies by region and timescale, but progress demonstrates adaptability. The lake's ecosystem remains dynamic rather than static. Wildlife populations adjust continuously. Environmental stresses fluctuate. Human influence evolves through policy, technology, and cultural change. Understanding these ecological dynamics adds depth to the broader story of Lake Erie. Danger is not only about sudden events, it also involves long-term environmental conditions shaping how people interact with the water. And as awareness of ecological complexity has grown, coordinated safety systems and rescue capabilities have evolved alongside environmental monitoring, reflecting lessons learned from both natural variability and decades of human experience on the lake. For every storm that caught a vessel off guard, for every sudden wave that overwhelmed a small boat, For every moment when fog erased the horizon, or cold water shocked an unprepared swimmer, there has also been another story unfolding on Lake Erie. It is the story of response, of rescue crews launching into difficult conditions, of technology evolving not only to predict danger, but to answer it when prevention fails. The lake's history is not defined only by loss, it is also defined by adaptation. In the earliest decades of organised navigation on Lake Erie, rescue efforts were limited by distance, communication, and speed. When a vessel foundered in the 1800s, survivors depended largely on nearby ships or shoreline witnesses. There was no centralised emergency system, no coordinated maritime rescue authority covering the entire lake. If a ship went down beyond sight of land and no other vessel was within range, help often arrived too late, or not at all. Life-saving stations gradually appeared along parts of the Great Lakes in the late 19th century. These were often modest facilities staffed by crews trained to respond to maritime distress. Using rowboats, surfboats, and later motorised craft, they ventured into heavy conditions when necessary. Equipment included life rings, ropes, and eventually line-throwing devices. These early rescue crews operated under severe constraints. Limited communication meant they often relied on visual signals such as flares or distress flags. The formation of what would eventually become the United States Coast Guard marked a significant step in professionalising maritime rescue. Consolidation of life-saving services and revenue marine operations created a structured framework for lake-wide response. Canadian maritime authorities developed parallel systems on the northern shoreline. Over time, cooperation between the two countries strengthened coordination across Lake Erie's international boundary. Motorised rescue boats replaced oar-powered craft, dramatically increasing response speed. Engines allowed crews to cover greater distances more quickly. Hull design improved to withstand steep, short-period waves characteristic of Lake Erie. Self-righting rescue boats reduced risk to rescuers operating in rough seas. Communication technology transformed rescue capability. Radio systems allowed vessels in distress to broadcast mayday calls. Early marine radio channels standardized distress communication. Ships and shore stations monitored these frequencies continuously. Rapid reporting replaced reliance on visual signals alone. The introduction of distress beacons added another layer of safety. Emergency position, indicating radio beacons, or EPIRBS, transmit distress signals via satellite when activated. Personal locator. Beacons serve similar functions for individuals. These devices allow rescue agencies to pinpoint location more accurately, even in fog or darkness. Helicopter rescue capability further expanded response range. Air assets can reach stranded boaters faster than surface vessels in many situations. Helicopters equipped with hoists retrieve individuals directly from water or vessel decks. Thermal imaging cameras assist in locating persons in low visibility or nighttime conditions. Modern search and rescue operations integrate multiple technologies simultaneously. Radar tracks vessel positions. Automatic identification systems display commercial ship locations. GPS coordinates from distress calls feed directly into rescue planning software. Drift models incorporate wind, wave, and current data to estimate movement of persons in water. Lake Erie's shallow depth and relatively confined geography allow coordinated coverage by several rescue stations positioned strategically along the shoreline. Response time varies by location, but coverage density has improved significantly compared to historical eras. Training standards for rescue personnel emphasize physical endurance, technical proficiency, and risk assessment. Crews train in cold water survival, high wave navigation, helicopter coordination, and medical response. Rescue swimmers undergo rigorous preparation to operate in rough conditions. Public education campaigns complement rescue capability. Programs encourage boaters to carry marine radios, file float plans, and wear life jackets. Safety courses teach interpretation of weather forecasts and proper use of emergency equipment. Prevention remains the first objective. rescue stands as backup. Maritime safety advances also extend beyond rescue infrastructure. Vessel design improvements reduce accident likelihood. Self-bailing cockpits prevent water accumulation. Improved bilge pump systems remove intruding water quickly. Compartmentalized hull construction limits flooding spread. Navigation aids continue evolving. LED buoy lights increase visibility. Solar-powered systems ensure continuous operation. Electronic charting reduces grounding risk. Digital mapping updates more frequently than paper charts of earlier decades. Weather alert systems integrate with marine radios to broadcast automatic warnings. Boaters receive real-time updates about small craft advisories, gale warnings, and thunderstorm alerts. Smartphone apps provide similar notifications, expanding reach to recreational users. Safety regulations have adapted as well. Mandatory carriage requirements for life jackets, fire extinguishers, and signalling devices vary by vessel type and size. Enforcement by maritime authorities reinforces compliance. Accident investigations generate reports that inform regulatory updates. International cooperation plays a central role on Lake Erie. Joint exercises between United States and Canadian rescue agencies improve cross-border coordination. Shared communication channels allow rapid information exchange during emergencies. Statistical analysis of incidents informs resource allocation. Patterns in accident timing, location, and cause help determine where additional safety education or infrastructure may be needed. Data-driven strategies improve effectiveness. Rescue efforts also incorporate volunteer organizations. Coast Guard auxiliary units, local marine patrols, and boating safety groups contribute support. Community involvement increases awareness and expands surveillance capacity. Environmental monitoring intersects with rescue operations. Knowledge of current direction, Seiche behavior, and temperature profiles assists in predicting drift paths. This integration of environmental science and operational response represents decades of accumulated learning. Cold water survival education has become more prominent. Public campaigns emphasize that immersion risk extends beyond winter months. Demonstrations illustrate the immediate impact of cold water shock. Increased awareness encourages wearing flotation devices year-round. Advances in medical response improve post-rescue outcomes. Rescue vessels carry emergency medical equipment. Coordination with Shoreline hospitals ensures rapid transfer. Training in hypothermia management and trauma care enhances survival rates. Commercial shipping safety protocols also evolved in parallel. Mandatory reporting of mechanical issues, structured watch schedules to reduce fatigue, and strict weather routing policies decrease large-scale incident probability. Rescue agencies coordinate closely with commercial operators during emergencies. Technology continues advancing. Unmanned aerial systems or drones are increasingly used in search operations. They provide overhead visibility in conditions where aircraft deployment might be impractical. High-resolution cameras assist in locating distressed individuals quickly. Despite these advances, rescue operations remain challenging. Steep waves, cold water, and sudden storms test equipment and personnel alike. Rescue crews accept inherent risk when launching into adverse conditions. Response culture on Lake Erie reflects accumulated history. Each generation learns from previous incidents. Safety bulletins reference past cases. Training scenarios simulate documented events. Institutional memory strengthens preparedness. Survival statistics have improved over time. Fatality rates relative to vessel traffic have declined compared to earlier centuries. Technology, regulation, education, and professionalization all contribute to this improvement. Yet rescue systems function as a final safeguard, not a replacement for caution. Even the most advanced response network cannot eliminate all risk. Rapid deterioration of conditions can outpace response time. Lake Erie's story therefore includes both hazard and adaptation. Physical characteristics remain constant. Shallow depth, long fetch, variable weather. human response evolves continuously to match those conditions. And when comparing Erie to its neighbouring Great Lakes, it becomes clearer how these physical traits, combined with heavy usage and history, contribute to its statistical standing among them. When people hear that Lake Erie is often called the deadliest of the Great Lakes, the instinctive reaction is sometimes disbelief. After all, Lake Superior is larger, deeper, and colder. Lake Michigan sees heavy recreational traffic. Lake Huron has complex shorelines and islands. Lake Ontario connects directly to the Atlantic shipping corridor. Each lake carries its own risks, so understanding why Lake Erie stands out requires looking carefully at how these lakes differ, not just in size but in depth, weather interaction, shoreline population, and patterns of use. The most obvious distinction is depth. Lake Superior, the largest by surface area and volume, reaches depths exceeding 1,300 feet. Lake Michigan averages roughly 279 feet. Lake Huron averages around 195 feet. Lake Ontario averages more than 280 feet. Lake Erie, by contrast, averages only about 62 feet. That single number shapes much of its behaviour. Depth affects thermal inertia. Deep lakes warm slowly in summer and cool slowly in winter. Shallow lakes respond faster to atmospheric changes. Lake Erie warms earlier in the year than the others, which supports ecological productivity but also contributes to rapid weather responsiveness. When cold air masses arrive over warmer water, atmospheric instability increases. Storm formation becomes more likely. Wave characteristics also differ. On deeper lakes like Superior, waves tend to form longer swells. They can become extremely large during major storms, but their spacing often allows larger vessels to ride them more predictably. On Lake Erie, the shallow basin compresses wave energy. Waves often become steeper and more closely spaced. This creates challenging conditions for smaller vessels even when wind speeds are moderate compared with storms on deeper lakes. Water temperature influences survival outcomes as well. Lake Superior's cold water presents severe hypothermia risk year-round. However, its lower shoreline population means fewer people regularly exposed. Lake Erie's warmer summer water attracts more recreational activity, increasing exposure even if individual conditions may be less extreme. Population density around the lakes plays a significant role in accident statistics. Lake Erie borders several major urban centres: Cleveland, Toledo, Buffalo, and parts of the Detroit metropolitan area. Southern Ontario cities such as Windsor and communities near Toronto also interact heavily with the lake. Accessibility increases usage. Increased usage increases the absolute number of incidents, even if per capita risk may be comparable. Lake Michigan also borders major cities, including Chicago and Milwaukee, and sees heavy recreational traffic. However, its greater depth moderates some wave behaviour. That does not eliminate danger, but it produces different patterns. Lake Huron presents navigational complexity due to numerous islands, especially in Georgian Bay. Fog and navigation challenges there are well documented, yet population distribution around Huron is less dense overall compared with Erie's southern shore, influencing total incident counts. Lake Ontario, though smaller in surface area than Erie, is deeper and somewhat more sheltered from long-fetch west-east wind alignment. It still experiences significant storms, but its depth alters wave development. Shipping traffic patterns also vary. Lake Erie serves as a major corridor connecting upper Great Lakes shipping to the Welland Canal and onward to the St. Lawrence Seaway. High commercial traffic historically increased exposure. While modern shipping safety has improved, historical accident totals remain part of the lake's reputation. Fishing patterns differ as well. Lake Erie's productivity supports major recreational and commercial fisheries. Concentrated fishing activity means more small boats offshore regularly. Lakes with lower fishing intensity may see fewer such exposures. Seasonal ice cover provides another comparison point. Lake Erie typically freezes more extensively than deeper lakes because shallow water cools quickly. Ice can reduce wave action, but introduces other hazards such as unstable ice sheets and early season boating risks during freeze-thaw cycles. Water quality history distinguishes Erie too. The pollution crisis of the mid-20th century affected Erie more visibly than some other lakes. Algal blooms, oxygen depletion, and ecosystem stress influence public perception. Environmental recovery efforts improve conditions, but that historical memory persists. Seiches behaviour is particularly notable on Lake Erie, due to its basin shape and shallow depth. While Seiches occur on other Great Lakes, the amplitude relative to depth on Erie can produce significant shoreline water level changes quickly. Harbour conditions shift accordingly. Meteorological positioning matters. Erie lies directly along common west to east storm tracks across North America. Systems moving across the continent often interact with the lake. Its alignment with prevailing winds enhances fetch potential. Another factor involves recreational culture. Lake Erie's beaches, relatively warm summer water, and urban accessibility encourage swimming, boating, and water sports. Exposure frequency influences accident statistics. Search and rescue data show that while severe storms on Lake Superior sometimes produce dramatic individual incidents, Erie accumulates a higher number of smaller incidents over time. This cumulative effect contributes to its statistical ranking. Public perception of risk varies by lake. Superior carries a reputation for cold and depth that encourages caution. Erie's accessibility and summer warmth may reduce perceived risk, even though environmental variability remains significant. Technological advances affect all Great Lakes similarly. Improved forecasting, GPS navigation, radar, and rescue coordination. Yet local geography determines how those technologies translate into safety outcomes. Commercial shipping accident rates have declined across all lakes due to regulation and technology. Recreational boating incidents now constitute a larger proportion of reported accidents, especially on lakes with heavy population access like Erie. Environmental change also affects each lake differently. Climate variability influences ice cover duration, water temperature, and storm patterns across the system. Erie's shallow depth means it often shows these changes sooner. Comparative research among the Great Lakes continues. Scientists monitor water temperature trends, nutrient loading, species distribution, and weather interactions. These data inform both environmental management and safety planning. Educational outreach sometimes frames Erie not as uniquely dangerous in isolation, but as uniquely responsive. Rapid environmental response means conditions shift faster. Awareness rather than avoidance becomes the emphasis. Statistical context matters. Deadliest reflects cumulative fatalities historically, rather than constant high-risk conditions. Many safe days occur each year on all Great Lakes. Risk varies with preparation, weather, and activity. Comparisons also highlight resilience. Despite challenges, all Great Lakes support commerce, recreation, and ecological diversity. Safety improvements reflect continuous adaptation. Understanding differences among the lakes helps clarify why Erie's characteristics produce particular patterns. Shallow depth, long fetch alignment, dense shoreline population, high recreational use, and historical shipping intensity combine to shape its reputation. These comparisons also reinforce a broader theme. Natural systems differ in ways that matter operationally. Awareness of those differences supports safer interaction. And beyond physical comparisons, there remains a psychological dimension. How people perceive inland seas, how familiarity shapes caution, and how risk awareness evolves with experience, culture, and communication. When people stand on the shore of Lake Erie for the first time, the reaction is often surprise at its scale. The horizon stretches wide. On clear days, the opposite shore may be invisible. The surface can look indistinguishable from the ocean. Yet even with that visual resemblance, many people do not instinctively categorize it the same way they would categorize the Atlantic or Pacific. The word lake carries different psychological weight than the word sea. This distinction matters. risk perception is not determined solely by physical danger. It is shaped by language, familiarity, cultural narratives, and personal experience. Inland seas like Lake Erie exist in a psychological category that can reduce perceived threat even when environmental conditions are capable of producing serious hazards. One of the strongest influences on risk perception is naming. Oceans are commonly associated with powerful storms, hurricanes, tidal forces, and open water vastness. Lakes, by contrast, are often associated with summer recreation, swimming, and calm scenery. Even when a lake spans hundreds of miles, the word itself can imply containment and control. Lake Erie's designation as a lake subtly shapes expectations. Visitors may assume that because it is enclosed by land, it must be inherently more manageable than the ocean. There are no tides of significant range, there are no saltwater sharks, there are no named hurricanes making national headlines with satellite images, yet wind-driven waves, steep chop, fog, cold water, and Seiches operate regardless of terminology. Another psychological factor involves visibility of danger. Ocean risks are frequently dramatized in media. Documentaries show towering waves crashing against cliffs. News coverage highlights tropical cyclones. Large maritime disasters become part of global awareness. Inland lake incidents receive more localized coverage. As a result, the broader public may underestimate cumulative risk. Familiarity amplifies this effect. People living near Lake Erie often grow up visiting beaches, marinas, and waterfront parks. Childhood memories anchor emotional perception. A place associated with family outings feels less threatening than an unfamiliar coastline. This familiarity can encourage confidence, sometimes beyond what conditions justify. There is also the concept of control illusion. Individuals tend to perceive environments they can see across, drive around, or cross by boat in a day as more controllable. Lake Erie, though vast, is geographically bounded. Maps show clear edges. The shoreline is always somewhere in the distance. This boundedness may create a subconscious sense that escape or rescue is inherently close, even when waves, fog, or cold water complicate reality. Risk normalization plays a role as well. When people witness others boating, swimming, and fishing without incident, they infer safety. Visible recreational activity signals social approval. Crowded beaches create collective reassurance. The absence of visible crisis reinforces the belief that conditions are acceptable. Cognitive biases influence interpretation of warnings. When forecasts mention a small craft advisory, the phrase may not evoke strong imagery. It sounds technical rather than urgent. Some boaters interpret it as optional guidance rather than serious caution. The same wind speeds described as gale conditions may prompt stronger reaction because the terminology feels more dramatic. Probability perception further shapes behaviour. If severe accidents are statistically rare relative to total lake visits, individuals may discount risk entirely. The human mind often struggles to evaluate low probability but high impact events accurately. People tend to assume that because something has not happened to them personally, it is unlikely to happen at all. Optimism bias reinforces this pattern. Most individuals believe they are less likely than others to experience negative outcomes. A boater might acknowledge that storms can be dangerous, but assume they will recognize trouble early enough to avoid it. A swimmer might understand that currents exist but assume strong swimming ability compensates. Experience level interacts with perception in complex ways. Inexperienced individuals may overestimate risk due to uncertainty. Moderately experienced individuals sometimes underestimate risk because prior success builds confidence. Highly experienced individuals often regain cautious respect through accumulated observation of variability. Media framing influences perception too. When Lake Erie is described primarily as a summer recreation destination, risk messaging competes with promotional imagery. Tourism campaigns emphasize beaches and sunsets. Safety messaging must operate within that broader narrative. There is also a distinction between acute and chronic risk perception. Sudden storms represent acute risk. Pollution and algal blooms represent chronic environmental risk. People tend to respond more immediately to acute, visible threats than to gradual changes. A thunderstorm cloud prompts action faster than a water quality advisory. Group psychology affects inland sea perception as well. When multiple boats remain on the water despite increasing wind, individual operators may hesitate to return to shore, assuming others perceive conditions as safe. Social proof influences decision-making, sometimes delaying caution. Language differences between lake and sea appear in maritime training contexts. Sailors trained on oceans often approach large lakes with a mindset shaped by open water caution. Recreational users without that background may approach differently. Risk communication strategies increasingly account for these psychological factors. Visual tools, such as wave height graphics or real-time buoy data, translate abstract forecasts into concrete imagery. Public safety campaigns emphasize phrases like cold water kills to counter warm weather associations. Education programs also highlight comparison, demonstrating that Lake Erie can produce waves comparable to coastal systems under certain wind conditions helps recalibrate perception. Showing temperature charts that reveal how long water remains dangerously cold extends awareness beyond summer months. Cultural memory plays a role. Historic shipwreck stories sometimes fade over generations. Without active storytelling or museum exhibits, collective memory weakens. Renewed historical education reconnects communities with the lake's long record of both productivity and hazard. Personal experience strongly shapes perception. A boater who has endured a sudden squall often carries heightened caution thereafter. Direct exposure modifies risk assessment more effectively than statistics alone. Emergency responders often describe encountering individuals who did not anticipate conditions deteriorating so quickly. Post-incident interviews frequently reveal surprise rather than defiance. That surprise reflects a gap between expectation and environmental reality. Technology influences perception in two directions. On one hand, real-time data and forecasting improve awareness. On the other, technological reliance may foster overconfidence. If a smartphone displays calm radar imagery at departure, individuals may assume continued stability despite atmospheric uncertainty. Understanding psychological perception does not diminish the lake's physical hazards. It clarifies why those hazards sometimes translate into preventable incidents. Risk exists where physical conditions and human interpretation intersect. Lake Erie's inland status creates a unique balance. It is neither a small recreational pond nor an open ocean. It functions as a large freshwater sea within continental boundaries. Its physical behaviour reflects that scale, even if its name does not. Awareness of perception helps align behaviour with conditions. When individuals approach Lake Erie with the same respect they would give open coastal waters, safety margins improve. When familiarity overrides observation, risk increases. And as cultural understanding evolves through education, technology and experience, the lake continues to offer both opportunity and challenge, quietly reinforcing the lessons it has demonstrated across centuries of human interaction. Lake Erie does not announce its lessons in dramatic language. It does not issue speeches or explanations. It operates according to physics, chemistry and biology. Yet over time, patterns emerge. The lake behaves consistently within its own rules. People who spend enough time around it begin to recognize those patterns, sometimes through study, sometimes through experience, and sometimes through incidents that leave lasting impressions. One of the clearest lessons is that scale can be deceptive. From a beach, the lake may look calm and manageable. The horizon seems close enough to imagine reaching in a small craft. On many days, that assumption holds true, but scale on water operates differently than scale on land. There are no roads, no fixed reference points once offshore. Distance feels shorter than it is. Conditions that seem minor at the shoreline can intensify away from land. Another lesson concerns change. Lake Erie rarely remains static. Wind shifts, temperature gradients form, water levels rise and fall with Seiches, fog develops and dissipates. Waves build faster than expected when fetch aligns with sustained wind. People who treat any single moment as representative of the entire day often encounter surprise. Those who anticipate change tend to adjust more effectively. The lake also teaches that depth matters in ways not immediately obvious. Its shallow average depth makes it highly productive biologically. It warms quickly, it supports major fisheries, yet that same shallowness allows wind energy to influence the entire water column rapidly. Waves steepen, Seiches amplify, water temperature shifts more quickly than on deeper lakes. The characteristic that creates abundance also creates responsiveness. Cold water immersion provides another direct lesson. Comfort in the air does not equal safety in the water. Water temperature lags behind seasonal expectations. A warm spring day does not mean warm water. The human body reacts to cold water instantly. Preparation must account for that, even when conditions appear pleasant. History reinforces these points. Shipwreck records show recurring themes. Sudden storms, limited visibility, mechanical failure combined with rough seas. Modern technology has reduced fatalities, but it has not eliminated environmental forces. The lake does not adjust its behaviour based on improved equipment. It responds to wind and temperature as it always has. Familiarity offers its own instruction. Repeated exposure without incident can reduce vigilance. Yet each season brings variability. Weather patterns shift year to year. Algal blooms vary in intensity. Ice cover changes with climate trends. Assumptions based solely on past experience require periodic re-evaluation. Lake Erie also demonstrates interconnectedness. Pollution in one watershed affects water quality miles away. Agricultural practices inland influence algal bloom formation offshore. Wind patterns in one basin alter water levels in another. Actions taken along the shoreline ripple across the entire system. Wildlife patterns illustrate adaptation. Fish populations adjust to invasive species. Bird migration shifts with temperature trends. Ecosystems respond gradually, sometimes subtly. Observing these changes over decades highlights the lake's dynamic nature. Rescue systems and safety infrastructure reflect accumulated learning. Each improvement in forecasting, communication and training stems from prior challenges. Progress does not eliminate risk, it narrows the margin between incident and recovery. Another lesson involves balance between use and respect. The lake supports commerce, recreation and ecological diversity. These uses are not mutually exclusive, but they require awareness. High traffic increases exposure. Responsible operation reduces consequences. Statistics often label Lake Erie as the deadliest Great Lake. That label captures cumulative history rather than constant peril. The lake experiences many calm days, beaches fill with families, boats travel without incident. The lesson is not that the lake is perpetually hostile, it is that variability defines it. Preparation becomes a recurring theme, checking forecasts more than once, wearing flotation devices consistently, maintaining equipment regularly, observing subtle environmental cues. These actions represent responses to lessons learned over generations. Lake Erie teaches that perception and reality sometimes diverge. The word lake may imply gentleness. Physical conditions may contradict that assumption. Aligning perception with physical behaviour improves safety outcomes. There is also a lesson in humility. No amount of experience eliminates uncertainty entirely. Weather models improve but remain probabilistic. Equipment advances but can fail. Human judgment evolves but is never infallible. Recognizing limits encourages cautious decision-making. At the same time, the lake demonstrates resilience. Environmental recovery after severe pollution shows capacity for renewal. Fisheries rebound under management. Wildlife returns when habitat improves. Resilience does not negate vulnerability, but it highlights responsiveness to positive action. Seasonal cycles reinforce patience. Ice forms and melts, water warms and cools, storm frequency rises and falls, patterns repeat with variation. Observing these cycles fosters understanding beyond isolated events. Lake Erie's lessons extend beyond boating or fishing. They illustrate broader principles of environmental interaction. Natural systems respond to physical laws consistently. Human systems adapt gradually. Outcomes depend on how well adaptation keeps pace with variability. Communities along the shoreline integrate these lessons into culture. Safety signage at beaches, marina bulletins about changing conditions, fishing advisories based on oxygen levels or toxin monitoring. Education reflects accumulated knowledge. The lake does not demand avoidance, it invites participation. But participation carries responsibility. Understanding physical characteristics, environmental dynamics, and psychological perception reduces unnecessary risk. In many ways, the lake teaches through contrast. Calm mornings that turn into rough afternoons demonstrate responsiveness. Clear water years followed by bloom-heavy summers demonstrate variability. Mild winters contrasted with severe storm seasons illustrate climate fluctuation. These patterns encourage attentiveness rather than alarm. Awareness does not require fear, it requires consistency. Small preventive actions repeated over time reduce the chance that environmental variability turns into incident. Ultimately, Lake Erie's long record of shipwrecks, storms, blooms, rescues and recoveries reflects a relationship between humans and a dynamic inland sea. The lake behaves according to its design. People adjust, sometimes successfully, sometimes after learning difficult lessons. And as that relationship continues, reflection becomes part of understanding, not to conclude the story, but to carry forward what observation and experience have revealed about water, weather, and the way we respond to both. If you spend enough time thinking about Lake Erie, a quiet realization starts to settle in. The lake has never been static. Long before modern boats, radar systems, environmental monitoring, or shoreline cities, it followed the same physical rules it follows now. Wind moved across it. Temperature shifted with seasons, currents formed, water levels oscillated, ecosystems adapted. Human presence introduced new variables, but the underlying behaviour remained grounded in physics and natural cycles. Looking at the lake today, it is easy to focus on individual hazards. Waves that build quickly, storms that develop faster than expected, cold water that demands respect even when the air feels comfortable, pollution challenges that took decades to address. Each of these deserves attention on its own. Yet together they point towards something broader, the importance of understanding how time shapes natural systems. Lake Erie's history stretches back thousands of years, formed by retreating glaciers at the end of the last ice age. Those glaciers carved basins, redirected rivers, and left behind a freshwater system that would eventually support ecosystems, indigenous communities, trade routes, industrial development, and modern recreation. The lake people experience today is only one moment in that longer timeline. When shipwreck records accumulate over centuries, they tell more than isolated stories. They reveal how human technology, training and perception evolved alongside environmental understanding. Early wooden schooners faced storms with limited forecasting. Steamships improved control but introduced mechanical complexity. Modern vessels incorporate satellite navigation, radar, and detailed weather models. Each step reflects adaptation over time rather than a sudden transformation. Environmental recovery illustrates a similar pattern. Pollution levels that once seemed overwhelming gradually declined through coordinated policy, improved wastewater treatment, agricultural management changes, and public awareness. The lake responded slowly but measurably. Fish populations recovered in many areas. Water clarity improved. Challenges remain, especially with nutrient runoff and algal blooms, but long-term trends show responsiveness when sustained effort continues. Time also reshapes climate patterns. Ice cover duration fluctuates. Average water temperatures shift incrementally. Storm intensity patterns evolve. These changes rarely occur overnight. They accumulate season by season. Observing them requires patience and consistent measurement. For individuals interacting with the lake, time influences perception too. A person visiting for the first time may see only calm water. Someone who has experienced a sudden squall carries a different awareness. Communities that have documented storms, shipwrecks, and environmental shifts across generations develop collective memory. That memory becomes part of local culture, influencing how people prepare. Respecting water in this context means recognizing variability. It does not imply fear. It means acknowledging that conditions can change, sometimes faster than expected. It means understanding that forecasts are tools, not guarantees. It means preparing equipment, monitoring updates, and remaining flexible when plans need adjustment. Respecting time means appreciating gradual processes as well as sudden events. Algal blooms do not form instantly. Ecosystem recovery does not happen in a single season. Safety habits develop through repetition. Environmental stewardship produces results over years rather than days. Respecting nature involves integrating both ideas. Natural systems operate on their own schedules. Human convenience does not alter wind patterns, temperature gradients, or biological cycles. Effective interaction requires alignment rather than control. Lake Erie demonstrates this alignment repeatedly. Commercial shipping schedules incorporate weather routing. Recreational boaters increasingly check buoy data before departure. Municipal water systems monitor toxin levels continuously. Fisheries management adjusts quotas based on population surveys. Each example reflects adaptation informed by observation. The lake also offers opportunity. Economic activity, recreation, ecological diversity, and scientific research all benefit from its presence. Balance emerges when opportunity is paired with awareness. Ignoring hazards reduces safety margins. Overestimating control leads to complacency. Technology continues evolving. Forecast models improve. Communication speeds increase. Safety equipment becomes more accessible. These developments enhance preparedness, but do not replace judgment. Technology works best when combined with experience and observation. Community plays a role as well. Shared information, local knowledge, and cooperative management across national borders strengthen resilience. Lake Erie connects multiple states, provinces, industries, and ecosystems. Collaboration reflects recognition that environmental systems rarely respect political boundaries. Education remains central. Teaching new generations about water safety, environmental stewardship, and historical context sustains progress. Awareness spreads through formal courses, community outreach, and everyday conversation. From a broader perspective, Lake Erie serves as a case study in how humans interact with large freshwater systems. It shows both vulnerability and adaptability. It highlights the importance of long-term thinking. It demonstrates how physical characteristics, human behaviour, and environmental policy intersect. Standing at the shoreline on a calm evening, the lake can appear unchanged. Yet beneath that surface, currents move, ecosystems adjust, and weather systems develop. Time continues shaping conditions whether visible or not. Understanding this continuity encourages steady attention rather than reactive response. Preparation becomes routine rather than exceptional. Environmental care becomes ongoing rather than occasional. The lake does not require constant vigilance every moment. Many days remain calm and welcoming. But consistent respect reduces the likelihood that sudden change catches anyone unprepared. And so, the story of Lake Erie continues not as a conclusion, but as an ongoing relationship between water, weather, wildlife, technology, and human experience. One that evolves gradually, shaped by observation, adaptation, and the quiet recognition that natural systems always deserve thoughtful attention.